Welcome to the introductory lesson of MongoDB for Developers and Administrators course offered by Simplilearn. We will start with the course objectives that describe what you will be able to do by the end of the course. Next, the MongoDB course overview is discussed, which will give you a strategic understanding of the course. Next, the value of this course to professionals as well as to organizations is discussed in detail. Following this, some other details on prerequisites for the course are covered. Finally, the lessons covered in this course are listed. Let us begin with the course objectives in the next screen. By the end of this course, you will be able to explain the functionalities of MongoDB as document database. Identify the benefits of MongoDB. Explain the different use cases of MongoDB. Explain how to create and manage different types of indexes in MongoDB for query execution. Explain how the replication and sharding features in MongoDB help in scaling read and write operations. Explain the administrative features of MongoDB. Let us take a look at the course overview in the next screen. This course will provide a detailed introduction of MongoDB and its features. It will explain the difference between NoSQL and the traditional Relational Database Management System, or RDBMS databases. It will provide a detailed introduction of MongoDB as a document database, explain MongoDB's role in the big data ecosystem, database scaling, replication, and sharding. It will further provide knowledge about how CRUD operations in MongoDB are performed, and the process of developing Java and Node.js applications. It also provides detailed steps of installing MongoDB in different operating systems and performing various functions. In the next screen, we will discuss how this course can add value to participants. This course is beneficial for professionals who administer, manage, and analyze large and complex data, such as database administrators, data analysts, and system and enterprise architects. Using MongoDB, database developers can perform the following tasks. Schema design, developing web application in Java and Node.js, developing mobile application in Java and Node.js. MongoDB allows data analysts to perform CRUD operations and analyze the data stored. System and enterprise architects can perform the following tasks using MongoDB's unique features. Analyze use cases, design system architecture, scale read and write functions, and optimize query performance. Let us look at the prerequisites for the course in the next screen. The basic prerequisite of the course is fundamental knowledge of programming language and Hadoop components. However, participants are expected to have a knowledge of SQL commands. In the next screen, we will focus on the list of lessons covered in this course. There are 7 lessons covered in this course. Take a look at the lesson names that are listed on the screen. Wishing you all the luck for this course. In the next lesson, we will focus on Introduction to NoSQL Databases. Hello, and welcome to Lesson 1 of the MongoDB Developer course offered by Simplilearn. This lesson provides an introduction to the NoSQL database. Let us explore the objectives of this lesson in the next screen. After completing this lesson, you will be able to explain what NoSQL databases are, explain the purpose of NoSQL databases, List the benefits of NoSQL database over traditional RDBMS database. Identify various types of NoSQL databases. List the differences between NoSQL and RDBMS, and explain MongoDB in relation to the CAP theorem. Let us begin with understanding what NoSQL is in the next screen. Traditionally, the software industries use relational databases to store and manage data persistently. Not only SQL or NoSQL is a new set of database that has emerged in the recent past as an alternative solution to relational databases. Carl Stroge introduced the term NoSQL to name his file-based database in 1998. NoSQL refers to all databases and data stores that are not based on the Relational Database Management Systems or RDBMS principles. It relates to large data sets accessed and manipulated on a web scale. NoSQL does not represent single product or technology. It represents a group of products and various related data concepts for storage and management. NoSQL was a hashtag that was chosen for a tech meetup to discuss the new databases. We will continue our discussion on NoSQL in the next screen. Typically, NoSQL does not have a prescriptive definition. The common characteristics of a NoSQL database are as follows. It does not use the relational model. It runs well on clusters. It mostly has an open source. It is built for the new generation web applications. It is schema-less. We will discuss the purpose of using NoSQL in the next screen. With the explosion of social media, user-driven content has grown rapidly and has increased the volume and type of data that is produced, managed, analyzed, and archived. In addition, new sources of data, such as sensors, global positioning systems or GPS, automated trackers, and other monitoring systems generate huge volumes of data on a regular basis. These large volumes of data sets, also called big data, have introduced new challenges and opportunities for data storage, management, analysis, and archival. In addition, data is becoming increasingly semi-structured and sparse. This means that RDBMS databases, which require upfront schema definition and relational references, are examined. To resolve the problems related to large volume and semi-structured data, a class of new database products have emerged. These new classes of database products consist of column-based data stores, key-value pair databases, and document databases. Together, these are called NoSQL. The NoSQL database consists of diverse products, with each product having unique sets of features and value propositions. In the next screen, we will identify the difference between NoSQL and RDBMS. NoSQL differs from RDBMS in terms of the following features. Data storage. In RDBMS, data is stored in a relational model in tabular format with numerous rows and columns. Rows contain information about an item type, and columns contain various values attributed to the item. For example, a row may contain information about an item, and the columns will contain specific information, such as model, date of manufacture, color, and so on. NoSQL comprises a host of different databases with different data storage models. Schemas and flexibility. Each record in an RDBMS follows a fixed schema. The columns are defined and locked before data entry. In addition, each row contains data for each column. Although this format can be modified, it will require altering the entire database and going offline. On the other hand, schemas in NoSQL are dynamic. You can add columns anytime. Unlike RDBMS, each row need not contain data for each column. Scalability. RDBMS supports vertical scaling. Typically, to handle more data, a bigger server is required. However, this will increase the cost. Although you can scale an RDBMS across multiple servers, it is a challenging and time-consuming process. Scaling is horizontal in NoSQL. You can scale across multiple servers. Multiple servers are cheap commodity hardware or cloud instances, which make scaling cost-effective compared to vertical scaling. Many NoSQL technologies automatically distribute data across different servers. Atomicity, consistency, isolation, durability, or ACID compliancy. Relational databases are mostly ACID compliant. However, most NoSQL databases compromise ACID compliancy for performance and scalability. In the next screen, we will discuss the benefits of NoSQL. The desired technical characteristics of an enterprise-class NoSQL solution are as follows. Primary and analytic data source capability. The first criterion of an enterprise-class NoSQL solution is it must serve as a primary or active data source that receives data from different business applications. It also must act as a secondary data source or analytic database that enhances business intelligence applications. From business perspective, the NoSQL database must be capable of quickly integrating all types of data, structured, semi-structured, or unstructured. In addition, it must be able to execute high-performance queries. Once all the required data is collected in the database, data administrators may want to perform an analysis in real time and in MapReduce form. An enterprise-class NoSQL database can easily handle such requests using the same database. It does not require loading the data into a separate analytic database for analysis. Big data capability. NoSQL databases are not restricted to working with big data. However, an enterprise-class NoSQL solution can scale to manage large volumes of data from terabytes to petabytes. In addition to storing large volumes of data, it delivers high performance for data velocity, variety, and complexity. Continuous availability or no single point of failure. To be considered enterprise class, a NoSQL database must offer continuous availability with no single point of failure. Moreover, rather than providing the continuous availability feature outside the software, the NoSQL solution delivers inherent continuous availability. The NoSQL databases must include the following key features. All nodes in a cluster must be able to serve read request even if some machines are down. Must be capable of easily replicating and segregating data between different physical shelves in a data center. This helps avoid hardware outages. Must be able to support data distribution designs that are multi-data centers, on-premises, or in the cloud. Multi-data center capability. Typically, business enterprises own highly distributed databases that are spread across multiple data centers and geographic locales. Data replication is a feature offered by all legacy RDBMS. However, none can offer a simple mode of data distribution between various data centers without any performance issue. Simple method includes the ability to handle multiple data centers without concerning about the occurrences of the read and write operations. A good NoSQL enterprise solution must support multi-data center deployment and must provide configurable option to maintain a balance between performance and consistency. Easy replication for distributed location independent capabilities. To avoid data loss affecting an application, a good NoSQL solution provides strong replication abilities. These include a read anywhere and write anywhere capability with full location independent support. This means you can write data to any node in a cluster, have it replicated on other nodes, and make it available to all users irrespective of their location. In addition, The right capability on any node must ensure that the data is safe in the event of a power failure or any other incident. No need for separate caching layer. A good NoSQL solution is capable of using multiple nodes and distributing data among all the participating nodes. Thus, it does not require a specific caching layer to store data. The memory caches of all participating nodes can store data for quick input and output or I/O access. NoSQL database eliminates the problem of synchronizing cache data with the persistent database. Thus, it supports simple scalability with fewer management issues. We will discuss some more benefits of NoSQL benefits in the next screen. Following are a few more benefits of NoSQL. Cloud ready. As adaptation of cloud infrastructure is increasing day by day, an enterprise-class NoSQL solution must be cloud ready. A NoSQL database cluster must be able to function in a cloud setting, such as Amazon EC2, and also must be able to expand and contract a cluster when necessary. It also must support a hybrid solution where part of the database is hosted within the enterprise premise and another part is hosted on a cloud setting. High performance with linear scalability. An enterprise-class NoSQL database can enhance performance by adding nodes to a cluster. Typically, the performance of database systems may go down when additional nodes are added to a cluster. However, a good NoSQL solution increases performance for both read and writes operations when additional nodes are added. These performance gains are linear in nature. Flexible schema support. An enterprise-class NoSQL database offers a flexible or dynamic schema design to manage all types of data, structured, semi-structured, and non-structured. Therefore, the need to have different vendors to support the different data types does not arise. NoSQL databases may support various schema formats, such as columnar, bigtable, and document. Therefore, choosing an appropriate database based on application requirement is a key design decision. The flexible or dynamic schema support ensures that you can make schema changes to a structure without making the structure offline. This support is critical considering the near-zero downtime and round-the-clock availability for business applications. Support key developer languages and platforms. Ideally, an enterprise-class NoSQL solution must support all major operating systems. In addition, it must run on a product hardware that does not require any tweaks or other proprietary add-ons. The NoSQL database must provide client interfaces and drivers for all common developer languages. It must offer a structured query language or SQL or a similar language that helps store and access data in a NoSQL database. Easy to implement, maintain, and grow. A NoSQL database must be simple but robust. In other words, it must be easy to implement and use, and must offer sturdy functionality to handle various enterprise applications. In addition, the NoSQL vendor must supply good management tools that assist data professionals perform various administrative tasks, such as adding capacity to a cluster, running utility tasks, and so on. The NoSQL database must allow easy growth without making any change to the front end of the business application. Thriving open source community. For an open source NoSQL database, having a vibrant community is essential to make regular contribution to enhance the core software. Moreover, open source communities generally provide excellent quality assurance or QA testing. This sometimes eliminates the need for software companies to hire, train, and retain a QA team. To encourage a thriving open source community, include activities on mailing lists and technical forums, initiate technical discussions, and participate in conferences. In the next screen, we will discuss the various types of NoSQL databases. There are four basic types of NoSQL databases. 1. Key Value Database. It has a big hash table of keys and values. REAC, Tokyo Cabinet, Redis Server, Memcached, and Scalaris are examples of key value store. 2. Document-based database. It stores documents made up of tagged elements. Examples include MongoDB, CouchDB, OrientDB, and RavenDB. 3. Column-based database. Each storage block contains data from only one column. Examples are Bigtable, Cassandra, HBase, and Hypertable. 4. Graph-based database. It is a network database that uses nodes to represent and store data. Examples are Neo4j, InfoGrid, Infinite Graph, and FlockDB. The availability of choices in NoSQL databases has its own advantages and disadvantages. The advantage is it allows you to choose a design according to your system requirements. However, because you have to make a choice based on requirements, there is always a chance that the same database product may not be used properly. We will learn about the key value database in the next screen. From an application program interface or API perspective, a key value database is the simplest NoSQL database. This database stores every single item as a key with a value. You can get the value for a key, add a value for a key, or delete a key. The value is a blob that the database stores without knowing its content. The responsibility lies with the application to understand what is stored. Typically, key value databases use primary key access. Therefore, they generally offer enhanced performance and scalability. All key value databases may not have the same features. For example, data is not persistent in Memcached while it is in REAC. These features are important when implementing certain solutions. For example, you need to implement caching of user preferences. If you implement them in Memcached, you may lose all the data when the node goes down, and may need to get them from the source database. If you store the same data in REAC, you may not lose data, but must consider how to update the stale data. It is important to select a key value database based on your requirements. We will continue with the discussion on key value database in the next screen. The key value store does not have a defined schema. It contains client-defined semantics for understanding what the values are. A key value store is simple to build and easy to scale. It also tends to have great performance because the access pattern can be optimized to suit your requirement. The advantages of key value store include the following. Queries. You can perform a query by using the key. Even range queries on the key are usually not possible. Schema. Key value databases have the following schema. Key is a string, value is a blob. The client determines how to parse data. Usages. Key value databases are handy when you need to access data using a key. Key value type database suffer from major weaknesses. The disadvantages are as follows. It does not provide any traditional database capabilities, such as consistency when multiple transactions are executed simultaneously. These capabilities must be provided by the application itself. As the volume of data increases, maintaining unique values as keys becomes difficult. To address this issue, you need to use character strings that will remain unique among large sets of data. In the next screen, we will discuss document database. This NoSQL database type is based on the concept of documents. It stores and retrieves various documents in formats such as XML, JavaScript, object notation, or JSON, binary JSON, or BSON, and so on. These documents are self-descriptive, hierarchical tree data structures, which consists of maps, collections, and scalar values. The stored documents can be similar to each other, but not necessarily the same. It stores documents in the value part of the key value database. You can consider the document databases as key value stores where you can examine the values. In the next screen, we will focus on examples of document database. MongoDB is an example of document database that provides a rich query language and constructs elements such as database, indexes allowing easy transition from relational databases. MongoDB is capable of scaling out with many of the most useful features of relational databases, such as secondary indexes, range queries, and sorting. MongoDB has many useful features, such as built-in support for map-reduce style aggregation and geospatial indexes. Apache CouchDB is a database that uses JSON for documents, JavaScript for map-reduce indexes, and regular HTTP for its API. In the next screen, we will learn about column-based database. Column-based databases store data in column families as rows. These rows contain multiple columns associated with a row key. Column families are groups of related data that is accessed together. For example, you may access customer profile information at the same time, but not their order history. Each column family is like a container of rows in an RDBMS table, where the key identifies the rows. Each row consists of multiple columns. However, the various rows need not have the same columns. Moreover, you can add a column to any row at any time without adding it to other rows. In the next screen, we will continue our discussion on column-based database. The goal of a column-based database is to efficiently read and write data to and from hard disk storage to quickly return a query. In this database, all column 1 values are physically together, followed by all the column 2 values. The data is stored in record order so that the 100th entry for column 1 and the column 2 are from the same input record. This allows you to access individual data elements, such as customer name, as a group in columns, rather than individually row by row. The compression permits columnar operations like min, max, sum, count, and average to be performed very rapidly. A column-based database management system, or DBMS, is self-indexing. Therefore, it uses less disk space than an RDBMS containing the same data. We will continue our discussion of column-based database in the next screen. The diagram provided on the screen depicts that data is getting stored in column rather than row format. It shows columns for the same column family are stored together in one file on the hard disk. Therefore, these data can be retrieved fast in an efficient manner. In the next screen, we will focus on an example of column-based database. Cassandra is one of the popular column-based databases. Cassandra is fast and easily scalable with write operations spread across the cluster. The cluster does not have a master node, hence any node can handle the read and write operations. In the next screen, we will discuss graph database. There are no isolated pieces of information, but rich, connected domains in this connected world. Therefore, only those databases that treat relationships as a core aspect of their data model can efficiently store, process, and query connections. In comparison to other general-purpose databases, a graph database makes relationships readily available for any join-like execution. Accessing those already persistent connections allow you to quickly access millions of connections per second per core. A graph database lets you store data and its relationships with other data in the form of nodes and edges. Each relation can have a set of properties. Edges have direction, which has its own significance, and enable you to explore the relationship in both the direction. All the nodes in the graph are organized by relationships that help explore interesting and hidden patterns between the nodes. We will continue our discussion on graph database in the next screen. The various available graph databases are Neo4j, Infinite Graph, OrientDB, and FlockDB. FlockDB only supports single-depth relationships or adjacency lists, where you cannot traverse more than one level deep for relationships. Neo4j is one of the most popular graph databases, which is ACID compliant. It is the product of the company Neo Technologies. It is Java-based but has bindings for other languages, including Ruby and Python. FlockDB was created by Twitter for relationship-related analytics. In the graph database, the labeled property graph model is used for modeling the data. It is same as the entity relationships or ER model used in RDBMS. The property graph contains connected entities such as the nodes, which can hold any number of attributes or key value pairs. In the next screen, we will discuss consistency, availability, and partition tolerance or CAP theorem. In a distributed system, the following three properties are important. Consistency. Each client must have consistent or the same view of the data. Availability. The data must be available to all clients for read and write operations. Partition toleration. System must work well across distributed networks. We will continue with the CAP theorem in the next screen. The CAP theorem was proposed by Eric Brewer. According to this theorem, in any distributed system, you can use only two of the three properties, consistency, availability, or partition tolerance simultaneously. That means to get a network partition, you may have to trade off availability of data or consistency. You may have to exchange durability for latency to survive failures with replicated data. Many NoSQL databases provide options for a developer to choose to adjust the database as per requirement. For this, understanding the following requirements is important. How the data is consumed by the system, whether the data is read or write heavy, if there is a need to query data with random parameters, and if the system is capable of handling inconsistent data. We will focus on consistency in the next screen. Consistency in CAP theorem refers to atomicity and isolation. Consistency means consistent read and write operations for the same sets of data, so that concurrent operations see the same valid and consistent data state without any stale data. Consistency in ACID means if the data does not satisfy predefined constraints, it is not persisted. Consistency in CAP theorem is different. In a single machine database, consistency is achieved using the ACID semantics. However, in the case of NoSQL databases, which are scaled out and distributed, providing consistency gets complicated. We will discuss availability in the next screen. According to the CAP theorem, availability means the database system must be available to operate when required. This means that a system that is busy, uncommunicative, unresponsive, or inaccessible is not available. If a system is not available to serve a request at a time it is needed, it is unavailable. In the next screen, we will discuss partition tolerance. Proven methods such as parallel processing and scaling are adopted as the model for scalability and performance instead of scaling up and building huge supercomputers. Instead of building giant computers, you can add several commodity hardware units in a cluster and make them work together. This is a cost and resource-effective solution. Cloud computing is a testimony to this solution. As NoSQL databases are distributed system by design, hence partitioning and occasional faults in a cluster are unavoidable. Partition tolerance or fault tolerance is the third element of the CAP theorem. Partition tolerance measures the ability of a system to continue its service when some of its clusters become unavailable. In the next screen, we will learn about MongoDB in terms of the CAP theorem. By default, MongoDB offers strong consistency. This means after you perform a write operation, you cannot read the same data until the write operation is successful. MongoDB is a single master system, and by default, all reads go to the primary node. Optionally, if you enable reading from the secondary node, MongoDB becomes eventually consistent and allows reading of out-of-date results. In addition, MongoDB handles network partition very well by keeping same data on multiple nodes or replica set. Therefore, MongoDB is a consistent and partition-tolerant database which comprises on the availability aspect. Here is a quick recap of what was covered in this lesson. NoSQL represents a class of products and a collection of diverse or related data concepts for storage and manipulation. NoSQL databases are used to efficiently manage large volume and semi-structured data. The four basic NoSQL database types are key value, document-based, column-based, and graph-based. According to the CAP theorem, a distributed computer system cannot provide all the three properties together: consistency, availability, and partition tolerance. This concludes the lesson on Introduction to NoSQL Databases. In the next lesson, we will discuss database for the modern web. Hello, and welcome to Lesson 2 of the MongoDB Administrator course offered by Simplilearn. This lesson will explain how the replication and Hello, and welcome to Lesson 5 of the MongoDB Developer course offered by Simplilearn. This lesson will explain how the Hello, and welcome to Lesson 2 of the MongoDB Administrator course offered by Simplilearn. This lesson provides an introduction to the MongoDB database and its key features. Let us explore the objectives of this lesson in the next screen. After completing this lesson, you will be able to describe what MongoDB is, identify the key features of MongoDB, explain MongoDB's core server and tools, explain how to install MongoDB on Windows and Linux computers, identify the steps to start the MongoDB server, identify the data types available in MongoDB, and identify the schema design and data modeling techniques in MongoDB. In the next screen, we will discuss MongoDB. MongoDB is a document-based database. The basic idea behind shifting from relational data model to a new data model is to replace the concept of a row with a flexible model, the document. The document-based approach allows embedded documents, arrays, and represents a complex hierarchical relationship using a single record. This is how developers using object-oriented languages want to represent their data. MongoDB is schema-free. The keys used in documents are not predefined or fixed. Without a fixed schema, massive data migrations have become unnecessary. While migrating data to MongoDB, any issues of new or missing keys can be resolved at the application level rather than changing the schema in the database. This offers developers the flexibility of working with evolving data models. In the next screen, we will discuss JSON, a data format used in MongoDB. JavaScript Object Notation, or JSON, is an open data interchange format that can be read by both human and computers. JSON is language independent. However, it uses conventions of the C family of languages, such as C, C++, and C#, Java, JavaScript, Perl, and Python. Because of these properties, JSON makes an ideal data interchange language. The main format used on the modern web is XML. Typically, JSON supports the basic data types, such as numbers, strings, Boolean values, arrays, and hashes. In the next screen, we will discuss JSON structures. JSON is built on the following two structures: a collection of name-value pairs, such as an object, record, struct, dictionary, hash table, keyed list, or associative array. An ordered list of values, such as an array, vector, list, or sequence. Typically, all modern programming languages support these universal data structures. In JSON, an object is considered as a set of name-value pairs which does not follow any order. Typically, an object is presented between a left brace and right brace. Each name in the object is followed by a colon, and the name-value pairs are separated by a comma. In the example of JSON given on the screen, the document has the ID field, which contains unique numbers to identify the document name field as MongoDB string, customers field as an array to represent customers of MongoDB. It also has an embedded document called application that contains information about different kinds of application built using MongoDB. In the next screen, we will discuss BSON. Binary JSON or BSON is a binary serialization format which is used for storing documents and making remote procedure calls in MongoDB. Similar to JSON, BSON allows embedding of documents and arrays within other documents and arrays. In addition, Bison supports extensions that represent data types that are not part of JSON. For example, Bison has a data type and a bin data type. Bison has the following three characteristics. Lightweight. Bison is lightweight. When used over the network, Bison manages to keep the overhead involved in processing extra header data to a minimum. Traversable. Bison is designed to traverse easily across network. This is a vital property in its role as the primary data representation for MongoDB. Efficient. Bison uses C data types that allow easy and quick encoding and decoding of data. MongoDB can build indexes inside Bison objects and match objects against query expressions on both top-level and nested Bison keys. We will discuss the structure of MongoDB in the next screen. The table given on the screen depicts the various SQL terminology and concepts, and the corresponding MongoDB terminology and concepts. In MongoDB, the table and view structure is known as collection. Typically, these collections group documents that are structurally or conceptually similar. MongoDB allows embedding a related document to one another. These documents are used to query related data. The data for a table in MongoDB are distributed among different shards, which is similar to the concept of partition in Relational Database Management Systems, or RDBMS. After grouping structurally similar documents into collection, MongoDB groups different collections into databases. For instance, a single instance of MongoDB is capable of hosting multiple independent databases. Ideally, you should store data related to a single application at one database. You need separate databases when storing multiple application or users' data on the same MongoDB server. In the next screen, we will examine a document store example. An example of an embedded document is given on the screen. In this example, a document is stored in the collection user for a person called Mark Taylor, who is 35 years old and has interest in long-distance running and mountain biking. This document also contains an embedded document called Favorites that displays the data about Mark Taylor's favorite color and sports. In the next screen, we will discuss MongoDB as a document database. The data model in MongoDB is document-based. Although documents provide rich structure, they need not conform to any pre-specified schema. In a relational database, rows are stored in a table, and each table has a strictly defined schema that specifies the permitted types and columns. If a row in a table requires an extra field, the entire table needs to be altered. MongoDB, on the other hand, groups documents into collections that do not follow any schema. Each individual document in a collection can have a completely independent structure. In practice, documents in a collection are relatively uniform. For example, if you are creating a collection review_comments for storing review comments given by the customer, then every document in this collection will have fields such as title, tags, comments, and so on. The lack of schema offers many advantages. First, since structure is defined by the application code, not the database, this speeds up initial application development when the schema tends to change frequently. Second, a schema-less model lets you represent data with variable properties. In the next slide, we will discuss transaction management in MongoDB. Compared to RDBMS, such as MySQL, which supports two-phase commit, MongoDB only supports a single-phase commit at each document level. A write operation in a single document is considered atomic in MongoDB, even if the operation alters multiple embedded documents. However, the entire operation is not atomic, and other operations may interleave. We will discuss easy scaling in the next screen. With the rapid growth of technology, dataset sizes are growing at a remarkable pace. Advances in sensor technology, the popularity of Internet-connected handheld devices have created a demand for more data storage with more databases capabilities. Even small-scale applications generate more data than many databases are capable of handling. As the amount of data that needs to be stored are growing, developers face the challenge of scaling their databases. Scaling is the core feature of MongoDB. You can add a new machine to the existing MongoDB cluster to expand its capacity. In the next screen, we will discuss how to scale up or scale out a database. Scaling a database involves two choices: scaling up or getting a bigger database, and scaling out or partitioning data across multiple databases. Scaling up is an easy but costly affair. Large databases are very expensive, and eventually a time may come when the purchased database too will be unable to handle the growing volumes of data, and a more powerful database is required. On the other hand, it is both extensible and cost-effective to scale out. You can buy commodity servers and add them to your cluster, thus add storage space and increase performance. In the next screen, we will discuss scale up or vertical scaling. You can easily scale a database by upgrading the hardware. If your application is running on a single node, you can add some combination of disk input-output per second, or IOPS memory, and CPU to enhance the database performance. The technique of enhancing a single node hardware is called vertical scaling or scaling up. Vertical scaling is simple, reliable, and cost-effective to some extent. If you are running on a physical hardware, you may face a situation where the cost of a more powerful server is not permitted. In such cases, you need to consider horizontal scaling or scaling out. In the next screen, we will learn about horizontal scaling. In horizontal scaling, database is distributed across multiple machines. You can use a commodity hardware for a horizontally scaled architecture. Thus, the cost for hosting the total data is reduced. In addition, the distribution of data across multiple machines mitigates the risk of failure. When you scale vertically, you need to deal with one machine when failure occurs. The failure may not impact your business if a copy of the data is saved on a replicated slave. However, failure of a single server may bring down the entire system. On the other hand, the failure in a horizontally scaled architecture is less disastrous because a single machine is only a small part of the entire system. MongoDB supports horizontal scaling. It uses a range-based partitioning mechanism called auto-sharding, which automatically manages data distribution across multiple nodes. In the sharding system, you can easily add new nodes. When a failure of the master node occurs, it does the failover to another replica set node. This whole sharding system is transparent to the client. The client does need to be aware whether it is single shard or a set of shards. In the next screen, we will discuss the features of MongoDB. Some of the key features of MongoDB are as follows. Ad hoc queries. MongoDB allows performing of search functions by field, range queries, and regular expression searches. Queries can return specific document fields and may include user-defined JavaScript functions. Querying. For document retrieval, MongoDB uses rich query language. It also allows you to write any complex condition to retrieve documents. Fast in-place updates. MongoDB allows you to choose write semantics, enable journaling, and thus control the speed and durability. All writes are sent across a Transmission Control Protocol, or TCP socket, and do not require a database response. To get a response, use the special safe mode of the drivers and perform a write. This generates a response acknowledging the receipt of the write with no errors. Server-side JavaScript execution. MongoDB uses JavaScript inquiries and aggregation functions such as MapReduce, which are sent to the database for execution. Capped collections. Capped collections are fixed-size collections supported by MongoDB. These collections maintain insertion order, and once the specified size has been reached, behaves like a circular queue. In the next screen, we will discuss secondary indexes. MongoDB allows implementation of multiple secondary indexes as B-trees. These B-tree indexes can be optimized for range scan queries and queries with sort clauses. MongoDB lets you create up to 64 indexes per collection. It supports indexes such as ascending, descending, unique, compound key, and geospatial. MongoDB uses the same data structure for indexes as most RDBMSs. In the next screen, we will learn about replication. MongoDB creates database replication using a topology called replica set. A replica set distributes data across various MongoDB nodes called shards for redundancy, and also automates failover when server or network outages occur. In addition, replication is used to scale database reads. For example, if your application is read-intensive, you can spread database reads across various nodes in the replica set cluster. Typically, a replica set contains one primary node and one or more secondary nodes. Similar to the master-slave replication, the primary node of a replica set supports both reads and writes. However, the secondary nodes support read-only. We will continue with replication in the next screen. The image on the screen depicts a working replica set. When the primary node fails, the cluster picks a secondary node and automatically converts it to primary. When the failed primary is restored, it acts as a secondary. We will discuss memory management in the next screen. MongoDB stores the data in memory-mapped files. By default, MongoDB uses all the system memory for these mapped files. This is the reason why MongoDB operations are fast. MongoDB allows its operating system to manage its memory. This design impacts its performances and operations. All extents are mapped to memory using mmap methods. In the image given on the screen, this mapping is depicted by the solid black lines connecting the mapped disk blocks to the virtual memory pages. In the next screen, we will discuss replica set. The replica set feature in MongoDB offers benefits such as redundancy and failover. When one node fails, it does not impact the entire database. If the failed node is a master node of the replica set, then MongoDB automatically converts another member of a replica set to the master. When replicating the data between master and slave nodes, choose whether you want a strong or delayed consistency. The replication process will keep replicated data on the nodes belonging to different data centers to protect the data in the case of natural disaster. In the next screen, we will discuss auto-sharding. MongoDB uses sharding for horizontal scaling. A shard is a master node with one or more slaves. You need to choose a shard key that determines the distribution of the collection data. The shard key splits the data into ranges and distributes them across multiple shards. MongoDB is spread over multiple servers and performs load balancing and/or data duplicating to keep the system up and running in case of hardware failure. Automatic configuration can be easily deployed, and new machines can be added to a running database. The diagram given on the screen represents documents distributed to different shards of the MongoDB cluster. In the next screen, we will discuss aggregation and MapReduce. Aggregation are operations used to analyze data sets and return calculated results. In MongoDB, you have a rich set of operations to perform aggregate calculation by analyzing the data sets. MapReduce is typically used for operations, such as batch processing of data and aggregation. MongoDB uses MapReduce operations to perform data aggregation. Typically, a MapReduce operation consists of two phases. In the map stage, documents are processed and one or more objects are produced for each input document. In the reduce stage, the outputs of the map operation are combined. Optionally, there can be an additional stage to make final modifications to the result. Similar to other aggregation operations, MapReduce can define a query condition to select the input documents and sort and limit the results. In the next screen, we will discuss collection and databases. A collection is a group of documents. If you compare a document in MongoDB to a row in a relational database, then a collection is like a table. Collections are not restricted by any schema. Therefore, documents within a single collection can have any shape. MongoDB groups collections into databases, and a single instance of MongoDB can host several databases, each a completely independent database. Having different types of documents in the same collection can be cumbersome for developers and administrators. Developers need to ensure that their queries retrieve specific documents or their application codes handle documents of different structure. A good practice is to store data of a single application in the same database. In the next screen, we will discuss schema design and modeling. The collections in MongoDB allows flexibility in document structure. This enables you to easily map a document to an entity or an object. Typically, all documents in a collection share a similar structure. The key challenge in data modeling involves maintaining a balance between the needs of the application, the performance capability of the database engine, and its data retrieval patterns. When designing a data model, you need to consider the application usage of the data, such as queries, updates, and data processing, along with its inherent structure. In the next screen, we will discuss reference data models. When designing data models for MongoDB applications, two things are important: the structure of documents and representation of the data relationships. References and embedded documents are the two tools that allow applications to represent data relationship. References use links from other documents to store relationships between data. Applications use these references to access the related data. These are called normalized data models. You can use normalized data models when embedding document results in data duplication does not give sufficient performance benefit, to represent complex many-to-many relationships, to model large hierarchical data sets. References provide more flexibility than embedding. However, client-side applications must trigger follow-up queries to resolve references. In other words, normalized data models can send more database queries from client to the database server. We will review an example of reference data model in the next screen. The diagram provided on the screen is an example of a reference data model which consists of 3 different collections named Offered Courses, Course_Detail, and Instructor. Each collection is dependent on the other collections. For example, if Offered Courses is dependent on Course_Detail and Instructor, then you need to create 3 different collections and provide the reference of Course_Detail and Instructor in the Offered Courses collection by storing their respective ID field. In the next screen, we will discuss Embedded Data Model. Embedded documents store related data in a single document structure and thus capture relationships between data. MongoDB allows embedding of document structures in a field or array within a document. Thus, these denormalized data models permit retrieval and manipulation of related data in a single database operation. You can use embedded data models when you have the following relationships between entities: contains and one-to-many. In these relationships, the many or child documents are viewed in the context of the parent documents. Typically, embedding provides good read performance. It also allows request and retrieval of related data in a single database operation. Embedded data models allow updating of related data in a single atomic write operation. In the next screen, we will focus on an example of embedded data model. The diagram given on the screen is an example of an embedded data model. In this diagram, the outermost document, Offered Course, contains 2 embedded document, Course Detail and Instructor. Course Detail has the fields, topic, and duration, while Instructor has the field's name and year of experience, or YOE. In the next screen, we will focus on data types. MongoDB supports other data types while retaining JSON's essential key-value pair characteristic. How values of each type are represented depends on the language used. Following is a list of the commonly supported data types. Null is used to represent both a null value and a non-existent field. For example, field X has null value. Undefined is used in documents. JavaScript has distinct types for null and undefined. For example, field X is undefined. Boolean is used to represent true and false values. For example, field X is a Boolean variable whose value is true. 32-bit integer cannot be represented on the shell. JavaScript supports only 64-bit floating point numbers. Hence, 32-bit integers will be converted to 64-bit. 64-bit integer. The shell cannot represent these and will display them using a special embedded document. 64-bit floating point number. All numbers in the shell must be of this type. We will continue with data types in the next screen. Here are a few more data types supported by MongoDB. Maximum value. BSON contains a special data type that represents the largest possible value. The shell does not support this type. Minimum value. BSON contains a special data type that represents the smallest possible value. The shell does not support this type. Object ID. Object ID data type is unique, fast to generate, and ordered. These consist of 12 bytes where the first 4 bytes represent the object ID creation time. String. BSON strings are UTF-8 compliant. Typically, when serializing and deserializing BSON, programming languages convert language strings to UTF-8 format. This allows easy storing of international characters in BSON strings. Symbol. Symbols are not supported by the shell. When the shell gets a symbol from the database, it converts it into a string. Timestamps. BSON offers a special timestamp for internal MongoDB use that is not associated with the regular date type. Note that within a single MongoDB instance, timestamp values are always unique. Date. Date in BSON is a 64-bit integer that denotes the number of milliseconds since the Unix epoch. It can represent a date range of about 290 million years into the past and future. Regular expression. Documents contain JavaScript's regular expression syntax. For example, X is the field whose value contain substring simply learn. We will discuss few more data types in the next screen. Following are some more data types supported by MongoDB. Code. Documents can contain JavaScript code. For example, logic inside function. Binary data. It is a string of arbitrary bytes. It cannot be manipulated from the shell. Array. Sets or lists of values can be represented as arrays. Courses is the field whose value is an array. This array holds 3 elements, PMP, Cloud, and MongoDB. Embedded document. Documents can contain entire documents, embedded as values in a parent document. For example, course_duration is the embedded document which has field name MongoDB. The value for this field is 24 hours. In the next screen, we will discuss the core servers of MongoDB. The core database server of MongoDB can be run as an executable process called MongoD or MongoDB.exe on Windows. The MongoD process receives a command to run the MongoDB server over a network socket through a custom binary protocol. The data files for a MongoD process are stored by default in the directory /data/db. You can run a MongoD process in several modes. The most common mode is the replica set. Typically, replica set configurations comprise 2 replicas and an arbiter process that reside on a third server. The auto-sharding architecture of MongoDB consists of MongoD processes configured as per-shard replica sets. It also consists special metadata servers called config servers. In addition, MongoS, a separate routing server, is used to send requests to the appropriate shard. MongoS queries from the application layer and locates the data in the sharded cluster to complete these operations. A MongoS instance is identical to any MongoDB instance. In the next screen, we will discuss the MongoDB tools. MongoDB tools consist of the following: JavaScript shell, database drivers, and command line tools. The Java script shell. The command shell in MongoDB is a JavaScript-based tool. It is used to administer the database and manipulate data. A Mongo executable loads the shell and connects it to a specified MongoDB process. In addition to inserting and querying data, the shell allows you to run administrative commands. Database drivers. The MongoDB drivers are easy to use. It provides an application program interface, or API, that matches the syntax of the language used while maintaining uniform interfaces across languages. Tengen, a company behind MongoDB, supports drivers for C, C++, C#, Erlang, Haskell, Java, Perl, PHP, Python, Scala, and Ruby. Command line tools. MongoDB contains the following command line utilities. MongoDump and MongoRestore are standard utilities that help back up and restore a database. MongoDump can save the data and the BSON format of MongoDB, and thus is used for backups only. This tool is used for hot backups and can be restored with MongoRestore easily. MongoExport and MongoImport are used to export and import JSON, comma-separated value, or CSV, and tab-separated value, or TSV, data. These tools help you get data in widely supported formats. You can use MongoImport for initial imports of large data sets. However, you need to adjust the data models for best results. In such a case, you can use a custom script to easily import the data through one of the drivers. MongoSniff is a wire sniffing tool used for viewing operations sent to the database. This tool translates the BSON that is transmitted to human-readable shell statements. MongoStat is similar to IOStat. MongoStat provides helpful statistics, including the number of operations per second. For example, inserts, queries, updates, deletes, and so on. It also provides information such as the amount of virtual memory allocated and the number of connections to the server. In the subsequent screens, we will learn how to install and start MongoDB on Linux and Windows. This demo will show the steps to install MongoDB on Linux. In this demo, you will learn how to install MongoDB on Linux machine. First, download the latest MongoDB binary for Linux platform. To download, type the command shown on the screen. After the MongoDB binary is downloaded, untar it by executing the command shown on the screen. Next, create a directory /MongoDB by executing the command make directory -p/MongoDB. Next, copy the untarred directory by executing command shown on the screen. To run MongoDB from anywhere in Linux, you need to add MongoDB installation path in the .bashrc file. To do so, execute the command vi/root/.bashrc. Next, type the two commands given on the screen. Note that your .bashrc file location may be different based on your username and profile. Reload the environment variable by executing the command source/root/.bashrc. Next, execute the command echo $MongoDB_home to verify whether the environment variable MongoDB_home has been set or not. This concludes the demo on installing MongoDB on Linux computer. This demo will show the steps to install MongoDB on a Windows computer. In this demo, you will learn how to install MongoDB on a Windows computer. MongoDB for Windows runs only on Windows Server 2008 R2, Windows Vista, or the later versions. The .msi installer includes all software dependencies. If you have an older version of MongoDB installed on your computer, the .msi file will automatically upgrade it to the latest version. To install, first go to the site given on the screen. In the Download and Run MongoDB page, scroll down and click Download to MSI, and then click Run. Once the MSI file is downloaded, the installation wizard opens automatically. Next, follow the default options on the wizard to install MongoDB. This concludes the demo on installing MongoDB on a Windows computer. This demo will show the steps to start MongoDB on Linux. In this demo, you will learn how to run the MongoD server and the Mongo shell on Linux. In this demo, you will learn how to run the MongoD server and the Mongo shell on Linux. To start the MongoD server, type MongoD in the command prompt. The MongoD script file is in the /bin directory of your MongoD home path. Once MongoD server starts running, open another terminal. To open the Mongo shell, type Mongo in the second terminal. In the Mongo shell, perform the MongoDB insert operation by executing the command given on the screen. To check whether document was inserted, use the find method on Courses collection. This concludes the demo on starting MongoDB on Linux. This demo will show the steps to start MongoDB on Windows. In this demo, you will learn how to run MongoD server and Mongo shell on Windows machine. To begin, navigate to the path C:/program files/MongoDB/server/3.0/bin. To start the MongoD server, double-click MongoD.exe. Once the MongoD server starts running, open another command prompt to open the MongoD shell. To open the Mongo shell, double-click the Mongo.exe in the same directory. To perform the insert operation in the Mongo shell, execute the command given on the screen. To check whether the document was inserted, execute the command db.courses.find. This concludes the demo on starting MongoDB on Windows. Let us discuss some use cases of MongoDB. Personalization. For any business, you need to have customer details, such as names, address, their online interactions, likes, and dislikes. Based on this information, you can predict the wants and needs of customers. MongoDB allows you to personalize customer experience in real time. It helps search through multiple lines of business, from holiday destinations to flights with different attributes, such as the time and number of flight connects, the size and model of a rental car, and so on. Customers can either log on or choose to surf through as a guest, view different products, pictures, and reviews. They may enter text notes about things they find, put up a comment. All these online activities amount to a large deal of unstructured data. A relational database would not be able to manage these online activities and normalize all customers, sessions, and product data through an extraction, transformation, and loading or ETL process. Mobile. Modern-day customers want everything on their smartphone. An RDBMS would not be able to handle these demands. MongoDB allows you to scale mobile applications to cater to millions of online users. Internet of Things, or IoT. The IoT is a world where all your physical assets and devices are connected for instant information sharing. Sensor-enabled devices generate huge volumes of data regularly, which cannot be managed by the traditional relational databases. MongoDB allows building of your own IoT suite. This helps you manage big data on your own. Real-time analytics. Most companies perform data analysis. Although many can act on data from months, weeks, or even days ago, few can respond to changes minute by minute or second by second because they cannot analyze semi-structured, unstructured, or geospatial data. The data changes faster than their systems can cope with. MongoDB allows data analysis in real time. In the next screen, we will review a few more use cases of MongoDB. Some more use cases of MongoDB are web application. MongoDB is a primary data store for web applications. A simple web application may require numerous data models for managing users, sessions, application-specific data, and uploads. The collection and document model of MongoDB helps these web applications manage data efficiently. As documents represent rich data structures, less collections can represent data. The same data will require more tables in a fully normalized relational model. In addition, dynamic queries and secondary indexes allow easy implementation of queries familiar to SQL developers. Finally, as a web application grows, MongoDB provides a clear path for scaling. Content management. Back in the year 2000, websites mostly contained static text content. With the ever-growing population of Internet users, you need an array of text, audio, video images, and social media to attract user attention. Adding new content, features, or attributes to a relational database is not easy. You need to take the databases offline to include any of these. With MongoDB, you can store and present any type of content, build new features, incorporate all kinds of data in a single database. Catalog. You use catalogs to organize stock keeping units or SKUs, forex trades, equipment, and everything else. However, you cannot easily add new items, such as new attributes or features, without impacting the database performance or making it offline. With MongoDB, you can do this easily. Online retailers have access to a lot of customer data. Smart retailers access these data to provide online shoppers a highly personalized and smooth shopping experience. Single View is the real-time views of your business that integrates all siloed data and display them in a single view. MongoDB allows you to build a single view of all your business data. Here is a quick recap of what was covered in this lesson. MongoDB is a document-based database that represents a complex hierarchical data relationship using embedded document model or using reference model. MongoDB uses JSON as the data format, which is based on a collection of name-value pairs, an ordered list of values. A collection in MongoDB is a table and view structure that groups structurally or conceptually similar documents. MongoDB supports auto-sharding to manage data distribution across multiple nodes. MongoDB uses replica sets to create redundancy and automates failover when server or network outages occur. This concludes the lesson MongoDB, a database for the modern web. In the next lesson, we will discuss CRUD operations in MongoDB. Hello, and welcome to Lesson 3 of the MongoDB Developer course offered by Simplilearn. This lesson will explain how to perform create, retrieve, update, and delete, or CRUD operations in MongoDB. Let us explore the objectives of this lesson in the next screen. After completing this lesson, you will be able to explain how to perform data modification in MongoDB, explain how to perform a batch insert, ordered bulk insert, and unordered bulk insert, explain how to insert documents to MongoDB collection, explain how to modify, update, upsert, and delete documents from MongoDB collection, identify the steps to use different query modifiers, such as find, query conditionals, queries, not modifier, regular expressions, and so on. Identify the steps to retrieve documents by using the find query or condition, cursor, batch insert. Identify the steps to retrieve documents for array fields. Identify the steps to perform a batch insert, ordered bulk insert, and unordered bulk insert. We will discuss data modification in the next screen. Data modifications are operations that involve creating, updating, or deleting data. These operations in MongoDB help modify the data of a single collection. Inserts is a basic data modification operation used for adding data to the MongoDB database. You can insert a document in a collection by using this method. For example, the query shown on the screen is used for inserting a document which has the name, address, courses, and offices fields. The db.collection.save method will update the document if it already exists, or will insert a new document. In the next screen, we will discuss what batch insert is. A batch insert is an operation that allows storing of multiple documents in a database at one time. You can send hundreds or thousands of documents in a batch at a time. This makes the whole insert operation faster than normal inserts, as multiple documents can be inserted simultaneously. A batch insert is performed as a single transmission control protocol, or TCP, request. This means that you do not need to make hundreds of individual requests to perform an insert. Batch insert eliminates the header processing activity for a message, and this reduces the insert time. Each document has a header which tells the database the kind of operation to be performed on a collection. Typically, batch inserts are used in applications for storing server logs and sensors data. To import raw data from Relational Database Management System, or RDBMS databases, such as Oracle or MySQL, instead of batch insert, use the command line tools such as Mongo import. At times, you may need to transform the data, like adding a custom _ID field before saving it to MongoDB. Remember, MongoDB does not accept messages which are heavier than 16 megabytes. Therefore, batch insert has a limit to how many messages it can include. In the next screen, we will discuss ordered bulk insert. With an ordered operations list, MongoDB performs the write operations in the list serially. If any error occurs during one of the write operations, MongoDB returns without executing the remaining write operations in the list. MongoDB groups an ordered operation by its type and contiguity. It groups contiguous operations of the same type together. For example, an ordered list contains two insert operations followed by an update operation, followed by another insert operation. MongoDB separates the operations into three groups. Group 1 will have the two insert operations, Group 2 will have the update operation, and Group 3 will have the last insert operation. This behavior of MongoDB is subject to change in future versions. In addition, each group can have a maximum of 1,000 operations. If the number of operations is more than 1,000, MongoDB divides the group into smaller groups, each having 1,000 or less operations. For example, if a bulk operation list contains 5,000 insert operations, MongoDB creates 5 groups, each having 1,000 operations. If you want to see how operations are grouped together and executed, enter the bulk.getOperations command after executing the bulk insert command. The example given on the screen is an ordered bulk insert where 3 documents will be inserted at one time. In the next screen, we will view a demo on how to perform an ordered bulk insert. This demo will show the steps to perform an ordered bulk insert in MongoDB. In this demo, you will learn how to perform the ordered bulk insert functions in MongoDB. To initialize a bulk operations builder for the collection items, execute the command given on the screen. This returns an ordered operations builder, which maintains a list of all the operations to perform. To add 5 insert operations to the bulk object, use the bulk.insert method given on the screen. You can call the execute method on the bulk object to execute the operations in its list. Once you execute the method, it gives the message duplicate key error index. When you retry to execute the same command again, then MongoDB will not allow. You can call the execute method only once on the same bulk object. To verify the inserted documents, call the find method on the items collection. For example, execute the command given on the screen. Notice that all 5 valid documents are inserted successfully in the items collection. This concludes the demo on performing ordered bulk insert on MongoDB. In an unordered operations list, MongoDB can perform write operations in parallel in a random order. If an error occurs during a write operation, MongoDB will perform remaining write operations uninterrupted. When performing an unordered list of operations, MongoDB groups them. For executing an unordered bulk operation, MongoDB may reorder the operations in the list for performance enhancement. Therefore, the applications must not depend on the sequence of operations when performing unordered bulk operations. You can call bulk.getOperations to see how these operations are grouped together and executed by the MongoDB. The unordered bulk command given on the screen will insert 3 documents in one go without concerning about order of insertion. In the next screen, we will view a demo on how to perform an unordered bulk insert operation. This demo will show the steps to perform an unordered bulk insert in MongoDB. In this demo, you will learn how to perform the unordered bulk insert in MongoDB. You can first initialize a bulk operations builder for the collection items by executing the command given on the screen. This returns an unordered operations builder, which maintains a list of operations to perform. Add the 3 insert operations given on the screen to the bulk object using the bulk.insert method. Next, call the execute method on the bulk object to execute the operations in its list. To verify the inserted documents, call the find method on the items collection. All the 3 valid documents are inserted successfully in the items collection. This concludes the demo on performing unordered bulk insert in MongoDB. When an insert operation is executed, the language driver converts the data structure into binary JSON or BSON before sending to the database. The database looks for a _ID key and confirms that the document has not exceeded 16 megabytes. However, other than that, it does not perform any data validation and saves the document to the database as is. MongoDB supports different language drivers, which check for invalid data, such as whether the strings are UTF-8 compliant, and filter out unrecognized data types before sending them to the database. If you are unsure about the driver you are using, start the database server with the Object Check option. This will examine the structural validity of each document before inserting them in the database. MongoDB does not perform any code execution on inserts, hence is not vulnerable to traditional injection attacks. In the next screen, we will view a demo on how to perform an insert operation. This demo will show the steps to perform an insert operation in MongoDB. In this demo, you will learn how to perform the insert function in MongoDB. First, launch the Mongo shell by typing Mongo in the terminal. To get the list of different databases, execute command show database. To go to test database, execute the command use test. Next, to store a document about Simplilearn course offering, execute the command given on screen. To confirm whether collection courses is created, execute the command show tables. Notice how the courses are displayed in the list of all the collections. Next, to verify whether document is inserted, execute the command db.courses.find. You can see that the document is inserted. This concludes the demo on performing the insert function in MongoDB. Typically, a MongoDB query targets specific documents in a collection. These queries define the criteria or condition based on which MongoDB identifies the documents that need to be returned to the clients. A query may include a projection that defines the fields that match the document fields to return. You can choose to modify queries to impose limits, skips, and sort orders. In the query given on the screen, items is the collection. Available true is the query criteria. Item 1 is its projection, and limit 5 is the modifier. In the next screen, we will discuss how to specify a quality condition. The find_one method is used to find the first record in the document. If you want the results displayed properly formatted, also use the pretty method. For example, the query db.items.find.pretty method helps select all documents in a collection and are displayed in proper format. An empty query document selects all documents in the collection. For example, db.items.find with empty query clause query will find all documents in a collection. If you do not specify a query document to the find method, it is similar to triggering an empty query document. Therefore, the operation db.items.find is equivalent to the operation db.items.find with empty query clause. To specify an equality condition, use the query document field value. This selects all documents that contain the field with the specified value. Below is the example of equality condition used in MongoDB query. The query db.items.find available true retrieves all documents from where the available field has the value true. In the next screen, we will view a demo on how to retrieve documents by using the find query. This demo will show the steps to retrieve documents from MongoDB collection by using the find query. In this demo, you will learn how to retrieve documents from MongoDB collections using the find query. To retrieve documents from items collections, execute the query shown on the screen. Alternatively, you can use another query to retrieve the documents. To get all the documents whose sold quantity field value is less than 500, execute the query shown on the screen. You can use the AND conditions in the query parameter and execute the query shown on the screen. This retrieves only those documents which satisfy all the query conditions. This concludes the demo on retrieving documents from MongoDB collections using the find query. You can also specify conditions using query operators. The in modifier is used to query a variety of values for a single key. If you have more than one possible value to match a single key, use an array of criteria with in modifier. The first query example given on the screen is used to select all documents in the items collection where the value of the type field is either true or false. You can also trigger this query using the OR operator. However, it is recommended to use the in modifier operator when performing equality checks on the same field. Specify and conditions. You can use a compound query to specify conditions for more than one field in the documents of a collection. The logical conjunction AND is used to connect the various clauses of a compound query. This helps the query to select the documents that match all the specified conditions. In the second query parameter given on the screen, two conditions are specified. One for inequality match on the field available, and another for less than comparison match on the field sold quantity. This query selects all documents where the available field value is true and the value in the price field is less than 900. In the next screen, we will discuss the OR operator. The OR operator returns the value true when any of its expressions evaluate to true or accepts any argument expressions. You can use the OR operator to define a compound query where each clause are joined with a logical OR conjunction. This compound query selects all documents in the collection that match minimum one condition. In the example given on the screen, the query document selects all documents in the collection where the field sold quantity has a value greater than 500 or the value of the available field is true. In the next screen, we will discuss AND as well as OR conditions. If you include additional clauses, you can specify the exact conditions for matching a document. In the first example given on the screen, the compound query document selects all documents in the collection where the value of the available field is true and either the sold quantity has a value greater than 200 or the value of the item field is book. The NOT condition is a metaconditional operator. You can apply a NOT condition to any other criteria. In the second example given on the screen, the modulus operator, mod condition, queries the keys whose values, when divided by the first given value, shows a remainder of the second value. The query given on the screen will give you all those documents whose ID, when divided by 4, will not have any remainder. In the next screen, we will view a demo on how to retrieve documents by using Find One and OR conditions. This demo will show the steps to retrieve documents in MongoDB by using the conditions Find One and OR. In this demo, you will learn how to retrieve documents from MongoDB collections using Find One and OR conditions. If you want to get all the documents from items collection whose sold quantity field value is greater than equal to 500, execute the command shown on the screen. To retrieve only one document, execute the Find One method. For example, to fetch only one document which satisfy either both or at least one of the conditions, execute the command shown on the screen. If you replace Find One with Find in the same query, then it will give you all the documents which match both the conditions. You can use the conditions AND OR in the same query. This will fetch only a single matching document. For example, executing the query shown on the screen will fetch only one matching document. This concludes the demo on retrieving documents from MongoDB collections using Find One and OR conditions. Regular expressions are used in string matching of flexible items. For example, you want to find all items whose value starts with PE, such as pen and pencil. You can use a regular expression to do case-insensitive matching. For example, use the first expression given on the screen to search for all instances of pen or pencil. In addition, if you want to match any variation of the item, pen, you can continue to improve the regular expression. To search for any variation, use the second expression given on the screen. In the next screen, we will discuss array exact match. You can use equality matches to match a single element in the array field. If the array contains minimum one element with the specified value, these specifications match. In the example, db.items.find country_codes 5, the operation queries for documents that contain an array country_codes that contains 5 as one of its elements. You can also use an equality match to match a specific element of an array. For this, use the dot notation shown on the second query given on the screen. In the next screen, we will discuss array projection operators. MongoDB provides the following projection operators for fields containing arrays, lm_match, slice, and position operators. The first operation, shown on the screen, uses the slice projection operator to retrieve only the first two elements in the country_codes array. lm_match, slice, and positional operator can be used to return a subset of elements for an array key. The second operation shown on the screen uses lm_match to get that document in which the country_codes array field contains value greater than equal and less than equal to 6. In the next screen, we will view a demo on how to retrieve documents for array fields. This demo will show the steps to retrieve documents for array fields. In this demo, you will learn how to use the projection operators, lm_match, slice, and positional operator. To return the first three elements in the country_codes array, use the slice projection operator in the command shown on the screen. Notice that the query has returned only 3 elements for country_codes field. Next, use the lm_match query to find out the array element for which both conditions match. This query will only fetch those elements whose value is greater than equal to 3 and less than equal to 5. This concludes the demo on using the projection operators for array fields. Key value pairs express a query very well. However, they cannot represent all queries. The where clauses, which allow arbitrary execution of JavaScript as part of your query, can represent the queries that key value pairs fail to represent. The where clauses allow you to perform any logical execution within a query. For example, it allows you to return documents from the collection that have 2 different keys with the same value. The most common scenario is comparing the values for 2 keys in a document. For example, the first query shown on the screen has a list of items and will return documents where any 2 of the values are equal. If the function returns true, The document will be part of the result set. If it returns false, it will not be a part of the result set. You can also use strings to specify a where query. The two where queries shown on the screen are equivalent. In the next screen, we will discuss cursor. The database uses a cursor to return results from find. Typically, the client-side implementations of cursors allow you to control a query output. For example, you can limit the number of results, skip some results, sort results using keys, and perform other powerful operations. To create a cursor with the shell, add documents into a collection, perform a query on the documents, and then allocate the results to a local variable such as var. This allows you to look at one result at a time. Even if you store the results in a global variable or no variable, the MongoDB shell can iterate through and display the first few documents. To iterate through the results, use the next method on the cursor. If you want to check if there is another result, use hasNext. The example given on the screen shows what a typical loop-through results looks like. The cursor.hasNext method calls to check for the next result, and the cursor.next fetches it. At this point, the query is sent to the server. The shell fetches the first 100 results or the first 4 megabytes of results, whichever is smaller immediately, so that the next or hasNext clauses do not have to make trips to the server. After the client has run through the first set of results, the shell contacts the database and requests for more results. The process continues till the cursor is exhausted and all results are returned. We will continue with the cursor in the next screen. Typically, the most common queries have the options to limit the number of results returned, skip a number of results, and sort them. You must include these options before sending a query to the database. To set a limit to the number of results fetched, add the limit function to your call to find. For example, if you want the query to return only 3 results from the items collection, use the query statement db.items.find.limit3. Typically, limit sets an upper limit, not a lower limit. If the number of documents matching your query are less than the number specified in the limit function, then only those documents will be returned. The skip function is similar to limit. The query db.c.find.skip3 will skip the first 3 matching documents and return other matches. It will not return any documents if your collection contains less than 3 documents. The sort function takes 2 parameters. The first parameter is the field name on which sorting should be performed, and the second parameter is a key-value pairs, where keys are key names and the values are the sort directions. There can be 2 sort direction, 1 or ascending or -1 or descending. For instance, to sort the results by username in the ascending order and age in the descending order, use the query given on the screen. In the next screen, we will view a demo on how to retrieve documents using cursor. Typically, the most common queries have the options to limit the number of results returned, skip a number of results, and sort them. You must include these options before sending a query to the database. To set a limit to the number of results fetched, add the limit function to your call to find. For example, if you want the query to return only 3 results from the items collection, use the query statement db.items.find.limit3. Typically, limit sets an upper limit, not a lower limit. If the number of documents matching your query are less than the number specified in the limit function, then only those documents will be returned. The skip function is similar to limit. The query db.c.find.skip3 will skip the first 3 matching documents and return other matches. It will not return any documents if your collection contains less than 3 documents. The sort function takes 2 parameters. The first parameter is the field name on which sorting should be performed, and the second parameter is a key-value pairs, where keys are key names and the values are the sort directions. There can be 2 sort direction, 1 or ascending or -1 or descending. For instance, to sort the results by username in the ascending order and age in the descending order, use the query given on the screen. In the next screen, we will view a demo on how to retrieve documents using Cursor. This demo will show the steps to retrieve documents from MongoDB using Cursor. In this demo, you will learn how to retrieve documents using the Cursor function. To retrieve all documents from items collection, execute the query db.items.find method. Notice that 5 documents are returned. If you want to skip some documents from the result set, use the skip function. For example, to skip 4 documents, execute the command db.items.findMethod.skip4. Notice that this query has skipped 4 documents and returned only 1. Similarly, to limit the number of documents being returned from the result set, use the limit function. For example, to limit the number of returned documents to 2, execute the command db.items.findMethod.limit2. Notice that this query has returned the first 2 documents from the list of 5 documents. You can use the cursor to iterate the documents to limit the number of results, skip some results, and sort results by any combination of keys in any direction, and perform other powerful operations. Let us first create a variable cursor and assign the result set to it. To do so, execute the command given on the screen. You can iterate the list of documents by using the while loop and the method hasNext to check whether the list of documents contains documents. If hasNext returns the value true, then execute the query to retrieve the next document from the list and assign it to a new variable. To get the print item and sold quantity fields for each document of the items collections, execute the commands given on the screen. Similarly, you can perform any mathematical or transformation operation here. Notice the output displayed on the terminal. The item and sold quantity fields for each document of the items collections are displayed. This concludes the demo on retrieving documents using Cursor. You can combine the limit, skip, and sort methods for pagination. For example, suppose a buyer searches for mobile on your online store. If you want to display 25 results sorted by price from high to low per page, you have to perform the first query shown on the screen. To display the next page for more results, you can add a skip to the query. For example, use the second query shown on the screen. This will skip the first 25 matches, which they saw on page 1. However, including large skips may slow down the display, hence must be avoided. In the next screen, we will discuss how to avoid larger skips. Using pagination, you can control the number of documents being returned by the find query. You can use the limit and skip functions to achieve pagination. In addition, you may perform pagination without using skips depending on your query. For example, to display the first page of a query result in the descending chronological order, use the first query given on the screen. Next, you can set the date value of the last page as the criteria for getting the next page. The second example given on the screen presents a pagination query without using a skip. In the next screen, we will discuss Advanced Query option. There are two types of queries executed by MongoDB, plain and wrapped. MongoDB wraps query into larger document by specifying many query options before sending them to server. Typically, language drivers help to add arbitrary options to queries. Apart from this, the following options help in adding to queries. Max scan integer. This specifies the maximum number of documents that are scanned for a query. Min document. This starts the criteria for querying. Max document. This ends the criteria for querying. Hint document. This tells the server which index to use for the query. Explain Boolean. This explains how the query will be executed, such as the indexes used, number of results to be displayed, the duration, and so on. It does not perform the actual query. Snapshot Boolean. This forces the query to use the index of the _ID field. In the next screen, we will discuss update. In MongoDB, the db.collection.update method is used to modify existing documents in a collection. This method defines the query criteria to identify the documents that needs update and all document options that affect its behavior. Operations performed by an update are atomic within a single document. For example, the update method is used by MongoDB to update the documents in a collection. This method has the following as its parameter: an update condition, an update operation, and an options document. You need to use a structure and syntax for specifying the update condition as you do for query conditions. You need to use multi-true to update multiple documents. In the next screen, we will view a demo on how to update documents in MongoDB. This demo will show the steps to update documents in MongoDB. In this demo, you will learn how to perform the update operation in MongoDB. You have a document which has the field item whose value is book. You need to update the document by adding the new fields, category, and details. To do so, execute the command given on the screen. The database response shows that your query has found and updated one document. To retrieve the updated document and verify that the fields are updated, execute the command given on the screen. This concludes the demo on updating a document in MongoDB. The set modifier specifies the value of a key. If a key does not exist, set creates it. This modifier updates schema or adds user-defined keys. You need to perform the following steps to use a set modifier. Step 1. Use update operators to change field values. You can use set operator to update the category and the details fields for the documents which has item field value as book. For documents with items equal to book, use the set operator to update the category and the details field as per the specified values. The first example given on the screen presents the update operator command. Step 2. Update an embedded field. You can use the dot notation to update a field within an embedded document. When using this, add the dotted field name in quotes. The second command updates the model field within the embedded details document. Step 3. Update multiple documents. To update the category field to stationery and the last modified field to the current date for all documents that have item field equal to pen, use the third command given on the screen. This will update multiple documents. In the subsequent screens, we will view demos on how to update documents in MongoDB. This demo will show the steps to update an embedded document in MongoDB. In this demo, you will learn how to update embedded documents in MongoDB. You need to update a document which has the embedded document called Details. This Details document has a field named Publisher. To update this document, execute the command given on the screen. The database response shows that your query has found and updated one document. To retrieve and verify the updated document, execute the command given on the screen. Next, execute the CLS command to clean up. This concludes the demo on updating embedded documents in MongoDB. This demo will show the steps to update multiple documents in MongoDB. In this demo, you will learn how to update multiple documents in MongoDB. You need to add the new field Online Sale and its value as true to all documents whose sold quantity field has value greater than 400. To update multiple documents with these fields, execute the command given on the screen. The database response shows that your query has found 3 documents and updated all of them. To retrieve the updated document and verify that all the 3 documents are updated, execute the command given on the screen. The output shows that a new field, Online Sale, is included in all 3 documents. This concludes the demo on updating multiple documents in MongoDB. Inc operator can be used for incrementing and decrementing numbers such as long, integer, or double. The first query given on the screen is incrementing the value of the sold quantity field by 1 for the document representing pencil. Note that you cannot apply ink modifier to non-numbers. The value of the ink key must be a number because you cannot increment a non-numeric value. To remove existing fields from the document, you can use unset modifier. To remove the sold quantity field for all the documents whose sold quantity field value is greater than 700, use the second query given on the screen. In the subsequent screens, we will view demos on how to perform an upsert and remove operation and replace existing documents with new documents in MongoDB. This demo will show the steps to use the ink modifier to increment and decrement a field value. In this demo, you will learn how to use the ink modifier to increment and decrement a field value. To find a document whose item field has the value pen, execute the query as shown. To increase the value of sold quantity for the document representing pen, execute the query given on the screen. To retrieve the document and verify that sold quantity field value is incremented by 1, execute the query given on the screen. To increase the value of sold quantity by 5, execute the query as shown on the screen. Next, to verify whether the value of sold quantity has become 709, execute the query as shown. If you want to decrease the value of sold quantity by -3, execute the query given on the screen. Next, verify whether the value of sold quantity has become 706 by executing the query shown on the screen. Next, remove a category field whose value is stationary by executing the query as shown on the screen. Finally, execute the query given on the screen to view and confirm that the category field is removed. This concludes the demo on using the ink modifier to increment and decrement a field value. This demo will show the steps to replace existing documents with new documents in MongoDB. In this demo, you will learn how to replace existing documents with new documents. To find a document whose item field has the value eraser, execute the query as shown. You need to replace this document with a new document which has the additional field sold quantity. To do so, execute the command given on the screen. Next, to retrieve the document and verify that it is replaced, execute the command as shown on the screen. The results will show that the old document is replaced by the new document with the additional field sold quantity. This concludes the demo on replacing existing documents with new in MongoDB. To add a new element into an array field, you can use the push function. The push function adds the element at the end of an array if the array already exists. Otherwise, it will create an array field and insert the element into that field. To add another ingredient, you can use the push function again. The query given on the screen is an example of how to use the push function to an ingredients key. When adding another email address, you can use the Add to Set modifier to prevent duplicate. In the next screen, we will discuss positional array modifications. Array modification is not easy when you want to modify some values when there are multiple values in an array. You can modify the array values in two ways: by position or by using the position operator, the $. For example, you are storing blog posts with comments in MongoDB. To increment the votes for the first comment, you can use the first command given on the screen. In many cases, it may not be clear which indexes of the array needs modification without first retrieving the document and examining it. To resolve this, MongoDB offers a positional operator, $, that helps identify the arrays matching the query document and updates them. For example, if you have a user called John who updates his name to Jim, you can replace it in the comments by using the positional operator shown on the screen. Note that the positional operator will update only the first match. Therefore, if John makes more than one comment in the blog, the name gets updated only in the first comment. In the subsequent screens, we will view demos on how to add elements into array fields using Add to Set modifier. This demo will show the steps to add elements into array fields in MongoDB. In this demo, you will learn how to add elements into existing array field. You can use the push modifier to add a new array field named Ingredients, whose value will be embedded to the document with the fields wood and graphite. To do so, execute the query given on the screen. The query response shows that one document is modified. Next, query the document and verify whether a new array field is added to the document. To do so, execute the command given on the screen. The document displayed shows that a new array field, Ingredients, is added. Next, push another element into this array, Ingredients, by executing the query statement given on the screen. Next, query the document and verify whether an element is added into the Ingredients array. Execute the query given on the screen. The result shows two elements in the Ingredients array. This concludes the demo on adding elements into existing array fields. This demo will show the steps to add elements into array fields in MongoDB. In this demo, you will learn how to use the Add to Set modifier to add elements into existing array fields. To use the Add to Set modifier and add a new element in the Ingredients Array field, execute the query statement given on the screen. The query response shows that one document is modified. Next, query the document and verify whether a new element is added to the array by executing the query given on the screen. The result shows 3 elements in the Ingredients Array. This concludes the demo on using the Add to Set modifier to add elements into existing array fields. This demo will show the steps to use Add to Set to ignore duplicate elements to be inserted into array fields. In this demo, you will learn how to use the Add to Set modifier to ignore duplicate elements inserted into the array field. You can use the Add to Set modifier to add the same element in the Ingredients Array field, again by executing the query statement given on the screen. The Add to Set modifier will ignore this document because the element in the Ingredients Array with the same value exists. The query response shows that none of the document is modified. This concludes the demo on using the Add to Set modifier to ignore duplicate elements inserted into the array field. An upsert is a special kind of update. If documents matching an update criteria are found, then they are updated. Otherwise, it will insert new documents into the collection. To use upsert, you need to pass upsert true as a parameter. The first command shown on the screen is an example of the upsert operation. By default, update operations modify only the first found document that matches the query criteria. If there are many matching documents, then they remain unchanged. To update all the documents that matches the query criteria, you can use true as the fourth parameter to update all of the documents. Multi-updates are the efficient operation for adding new feature to all the documents. Suppose, for example, you want to present a gift to every user on their birthday. You can use the multi-update command given on the screen to add a gift to their account. This would add the gift key to all user documents with birthdays on October 22, 1978. In the next screen, we will discuss removing documents in MongoDB. You can remove data from a collection using the remove method. The first command given on the screen is used for this purpose. However, this will only remove all of the documents in the courses collection, not the collection and indexes created. Optionally, the remove command treats a query document as its parameter. When this command is used, only those documents that match the query document criteria are removed. To remove documents from the items collection, where the value for item is bag, use the second command given on the screen. To remove a single document, call the remove method with the 2 parameters. The third command given on the screen is used to remove one document from the accounts collection where the dormant field equals true. To delete all documents from a collection, you can use the drop method. This will remove the entire collection, including the indexes. In the next screen, we will view a demo on how to perform an upsert and remove operation. This demo will show the steps to perform an upsert and remove operation in MongoDB. In this demo, you will learn how to perform an upsert and remove operation in the MongoDB. To insert a new document in the items collection, execute the query given on the screen. In the query, you are passing upsert true to perform the upsert operation as the fourth parameter. The right result shows that one document is upserted. To retrieve the upserted document, execute the command given on the screen. Next, you can drop the collection which is not present by executing the command db.item.drop. This will return false, indicating that remove operation has failed. To drop a collection which exists in the database, execute the db.courses.drop command. This will return true, indicating that remove operation is successful. This concludes the demo on performing an upsert and remove operation in the MongoDB. Here is a quick recap of what was covered in this lesson. Data modifications in MongoDB involve creating, updating, or deleting data. Using batch insert, you can send hundreds or thousands of documents in a batch at a time. MongoDB divides an ordered operation into groups containing a maximum of 1,000 operations. And unordered bulk inserts allow write operations in parallel in a random order. MongoDB allows you to specify conditions using query operators such as in, and, or. Cursors in MongoDB allows you to modify queries to impose limits, skips, and sort orders. You can use pagination to customize the display results for a search query. This concludes the lesson, CRUD Operations in MongoDB. In the next lesson, we will discuss indexing and aggregation in MongoDB. Hello, and welcome to Lesson 4 of the MongoDB Developer course offered by Simplilearn. This lesson will explain how to create and manage different types of indexes in MongoDB to execute queries faster. Let us explore the objectives of this lesson in the next screen. After completing this lesson, you will be able to explain how to create unique, compound, sparse, text, and geospatial indexes in MongoDB. Explain the process of checking the indexes used by MongoDB when retrieving the documents from the database. Identify the steps to create, remove, and modify indexes. Explain how to manage indexes by listing, modifying, and dropping. Identify different kinds of aggregation tools available in MongoDB. Explain how to use MapReduce to perform complex aggregation operations in MongoDB. We will begin with an introduction to indexing in the next screen. Typically, indexes are data structures that can store collections' data set in a form that is easy to traverse. Queries are efficiently executed with the help of indexes in MongoDB. Indexes help MongoDB find documents that match the query criteria without performing a collection scan. If a query has an appropriate index, MongoDB uses the index and limits the number of documents it examines. Indexes store field values in the order of the value. The order in which the index entries are made support operations, such as equality matches and range-based queries. MongoDB sorts and returns the results by using the sequential order of the indexes. The indexes of MongoDB are similar to the indexes in any other databases. MongoDB defines the indexes at the collection level for use in any field or subfield. In the next screen, we will discuss index types. MongoDB supports the following index types for querying. Default _ID. Each MongoDB collection contains an index on the default _ID field. If no value is specified for _ID, the language driver or the MongoD creates an _ID field and provides an object ID value. Single field. For a single field index and sort operation, the sort order of the index keys do not matter. MongoDB can traverse the indexes either in the ascending or descending order. Compound index. For multiple fields, MongoDB supports user-defined indexes, such as compound indexes. The sequential order of fields in a compound index is significant in MongoDB. Multi-key index. To index array data, MongoDB uses multi-key indexes. When indexing a field with an array value, MongoDB makes separate index entries for each array element. Geospatial index. To query geospatial data, MongoDB uses two types of indexes, 2D indexes and 2D sphere indexes. Test indexes. These indexes in MongoDB searches data string in a collection. Hashed indexes. MongoDB supports hash-based sharding and provides hashed indexes. These indexes the hashes of the field value. We will discuss the index types in detail later in the lesson. In the next screen, we will discuss the index properties. Following are the index properties of MongoDB. Unique indexes. The unique property of MongoDB indexes ensure that duplicate values for the indexed field are rejected. In addition, the unique indexes can be interchanged functionally with other MongoDB indexes. Sparse indexes. This property ensures that queries search document entries having indexed field. Documents without indexed fields are skipped during a query. Sparse index and the unique index can be combined to reject documents with duplicate field values and ignore documents without indexed keys. Total time to live, or TTL indexes. These are special indexes in MongoDB used to automatically delete documents from a collection after specified duration of time. This is ideal for deleting information, such as machine-generated data, event logs, and session data that needs to be in the database for shorter duration. In the next screen, we will discuss single field index. MongoDB supports indexes on any document field in a collection. By default, the _ID field in all collections have indexes. Moreover, applications and users add indexes for triggering queries and performing operations. MongoDB supports both single field or multiple field indexes based on the operations the index type performs. The command given on the screen is used to create an index on the item field for the items collection. In the next screen, we will discuss how to create single field indexes on embedded documents. You can index top-level fields within a document. Similarly, you can create indexes within embedded document fields. The structure shown on the screen refers to a document stored in a collection. In the document, the Details field depicts an embedded document that has two embedded fields, ISDN and Publisher. To create an index on the ISDN field and the embedded document called Details, perform the queries shown on the screen. In the next screen, we will discuss compound indexes. MongoDB supports compound indexes to query multiple fields. A compound index contains multiple single-field indexes separated by a comma. The command shown on the screen is an example of a compound index on two fields. This diagram depicts a compound index for the fields user ID and score. The documents are first organized by user ID, and within each user ID, scores are organized in the descending order. The sort order of fields in a compound index is crucial. The documents are first sorted by the item field value, and then, within each item field value, they are further sorted by the stock field values. For a compound index, MongoDB limits the fields to a maximum of 31. In the next screen, we will discuss index prefixes. Index prefixes are created by taking different combination of fields and typically start from the first field. For example, consider the compound index given on the screen. It has item in the ascending order and available in the ascending order as the index prefixes. MongoDB uses a compound index even if the find queries are for index prefixes fields. It uses indexes for querying the item field, the available field, and the sold quantity field. MongoDB cannot efficiently support the query on the item and sold quantity fields by using index prefixes, as it would be like using separate indexes for these fields. The item field is a part of the compound index and the index prefixes. Hence, the item field should be used in the find query of the index. We will discuss sort order in the next screen. In MongoDB, you can use the sort operations to manage the sort order. You can retrieve documents based on the sort order in an index. If you are unable to obtain the documents sorted from an index, the results will get sorted in the memory. Sort operations executed using an index show better performance than those executed without using an index. In addition, sort operations performed without an index gets terminated after exhausting 32 megabytes of memory. Typically, indexes store field references in the ascending or descending sort order. For single field indexes, MongoDB can traverse the index in either direction. Hence, the sort order is not important. However, for compound indexes, the sort order is important because it helps determine if the index can support a sort operation. In the next screen, we will discuss how to ensure that indexes fit in the random access memory, or RAM. To process query faster, ensure that your indexes fit into your system RAM. This will help the system avoid reading the indexes from the hard disk. To confirm the index size, use the query given on the screen. This returns the data in bytes. To ensure this index fits your RAM, you must have more than the required RAM available. In addition, you must have RAM available for the rest of the working set. For multiple collections, check the size of all indexes across all collections. The indexes and the working sets both must fit in the RAM simultaneously. In the next screen, we will discuss multi-key indexes. When indexing a field containing an array value, MongoDB creates separate index entries for each array component. These multi-key indexes in queries match array elements with documents containing arrays and select them. You can construct multi-key indexes for arrays holding scalar values, such as strings, numbers, and nested documents. To create a multi-key index, you can use the db.collection.createIndex method given on the screen. If the indexed field contains an array, MongoDB automatically decides to either create a multi-key index or not create one. You need not specify the multi-key type explicitly. In the next screen, we will discuss compound multi-key indexes. In compound multi-key indexes, each indexed document can have maximum one indexed field with an array value. If more than one field has an array value, you cannot create a compound multi-key index. An example of a document structure is shown on the screen. In this collection, both the product_ID and retail_ID fields are arrays. Therefore, you cannot create a compound multi-key index. Note that a shard key index and a hashed index cannot be a multi-key index. In the next screen, we will discuss hashed indexes in detail. The hashing function combines all embedded documents and computes hashes for all field values. However, it does not support multi-key indexes. Hashed indexes support sharding. These indexes use a hashed shard key to shard a collection. This ensures an even distribution of data. MongoDB uses hashed indexes to support equality queries. However, range queries are not supported. You cannot create unique or compound index by taking a field whose type is hashed. However, you can create a hashed and non-hashed index for the same field. MongoDB uses the scalar index for range queries. You can create a hashed index using the operation given on the screen. This will create a hashed index for the item's collection on the item field. In the next screen, we will discuss TTL indexes in detail. TTL indexes automatically delete machine-generated data. You can create a TTL index by combining the db.collection.createIndex method with the expire after seconds option on a field whose value is either a date or an array that contains date values. For example, to create a TTL index on the last modified date field of the event log collection, use the operation shown on the screen in the Mongo shell. The TTL background thread runs on both primary and secondary nodes. However, it deletes documents only from the primary node. TTL indexes have the following limitations. They are not supported by compound indexes, which ignores expire after seconds. The _ID field does not support TTL indexes. TTL indexes cannot be created on a capped collection because MongoDB cannot delete documents from a capped collection. It does not allow the createIndex method to change the value of expire after seconds of an existing index. You cannot create a TTL index for a field if a non-TTL index already exists for the same field. If you want to change a non-TTL single field index to a TTL index, first drop the index and recreate the index with the Expire After Seconds option. In the next screen, we will be discussing creating unique indexes. To create a unique index, use the db.collection.createIndex method and set the unique option to true. For example, to create a unique index on the item field of the items collection, execute the operation shown on the screen in the Mongo shell. By default, unique is false on MongoDB indexes. If you use the unique constraint on the compound index, then MongoDB will enforce uniqueness on the combination of all those fields which were part of the compound key. Unique index and missing field. If the indexed field in a unique index has no value, the index stores a null value for the document. Because of this unique constraint, MongoDB permits only one document without the indexed field. In case there are more than one document with a valueless or missing indexed field, the index build process will fail and will display a duplicate key error. To filter these null values and avoid error, combine the unique constraint with the sparse index. In the next screen, we will discuss sparse indexes. Sparse indexes manage only those documents which have indexed fields, even if that field contains null values. Sparse index ignores those documents which do not contain any index field. Non-sparse indexes do not ignore these documents and store null values for them. To create a sparse index, use the db.collection.createIndex method and set the sparse option to true. In the example given on the screen, the operation in the Mongo shell creates a sparse index on the item field of the items collection. If a sparse index returns an incomplete index, then MongoDB does not use that index unless it is specified in the hint method. For example, the second command given on the screen will not use a sparse index on the X field unless it receives explicit hints. An index that combines both sparse and unique does not allow collection to include documents having duplicate field values for a single field. However, it allows multiple documents that omit the key. In the next screen, we will view a demo on how to create compound, sparse, and unique indexes. This demo will show the steps to create compound, sparse, and unique indexes in MongoDB. In this demo, you will learn how to create compound, sparse, and unique indexes. To create an index on the customer_info collection, use the command shown on the screen. The retrieved result shows two indexes on the collection. You can create sparse indexes on the field which is not available in all the documents of the collection. To create a sparse index on the category field and initiate the index creation process in the background, execute the command given on the screen. The result shows 3 indexes on the items collection. To create a unique index on the item field of the collection, execute the command shown on the screen. Notice that 2 indexes are created on the item collection. This concludes the demo on creating compound, sparse, and unique indexes on the fields of a collection. Text indexes in MongoDB helps search for text strings in documents of a collection. You can create a text index for field or fields containing string values or an array of strings. To access text indexes, trigger a query using the text query operator. When you create text indexes for multiple fields, specify the individual fields or use the wildcard specifier $**. To create text indexes on the subject and content fields, perform the query given on the screen. The text index organizes all strings in the subject and content field, where the field value is either a string or an array of string elements. To allow text search for all fields with strings, use the wildcard specifier $**. This indexes all fields containing string content. The second example given on the screen indexes any string value available in each field of each document in a collection and names the indexes as text index. In the next screen, we will view a demo on how to create single field and text indexes in MongoDB. This demo will show the steps to create single field and text indexes in MongoDB. In this demo, you will learn how to create single field and text indexes. To create an index on the customer_info collection, use the command shown on the screen. The response from MongoDB lets you verify whether the index creation is successful or not. The result shows that number indexes after is 2, while number indexes before is 1. This indicates that the index is created. Alternatively, you can use another command to retrieve the list of all the indexes created for the particular collection. To retrieve all the indexes for the customer_info collection, execute the command shown on the screen. The output shows 2 indexes on the customer_info collection. The first index is the default index created on the _ID field. On the other hand, the second index is the one which you created on the customer_name field. By default, the name of the index will be fieldname_digit. You can create a text index on the field whose type is either a string or an array of string. Let us create a text index on the item field whose type is string by executing the command given on the screen. You can also provide a name to the index. Notice that the result shows 3 indexes on the customer_info collection. The name of the new index is item_index. The default language is English, and the index version is 2. This concludes the demo on creating single field and text indexes on a collection. MongoDB supports various languages for text search. The text indexes use simple language-specific suffix stemming instead of language-specific stop words, such as the, an, and. You can also choose to specify a language for text search. If you specify the language value as none, then the text index uses simple tokenization without any stop word and stemming. In the query given on the screen, you are enabling the text search option for the item field of the customer_info collection with Spanish as the default language. If the index language is English, text indexes are case insensitive for all alphabets from A to Z. The text index and the text operator supports the following: 2-letter language codes defined in ISO 639-1. Danish, Dutch, English, Finnish, French, German, Hungarian, Italian, Norwegian, Portuguese, Romanian, Russian, Spanish, Swedish, and Turkish. Note that a compound text index cannot include special index types, such as multi-key or geospatial index fields. In the next screen, we will discuss index creation. MongoDB provides several options to create indexes. By default, when indexes are created, all other operations on a database are blocked. For example, when indexes on a collection are created, the database becomes unavailable for any read or write operation until the index creation process completes. The read or write operations on the database queue allow the index building process to complete. Therefore, for index building operations which may consume longer time, you can consider the background operation and thus make MongoDB available even during the entire operation. The command given on the screen is used for this purpose. By default, background is false for building MongoDB indexes. We will discuss index creation further in the next screen. When MongoDB is creating indexes in the background for a collection, you cannot perform other administrative operations involving that collection. For example, you cannot perform tasks such as run, prepare database, drop the collection, or use the query db.collection.drop and run compact. If you perform any of these operations, you will receive an error. The index build process at the background uses an incremental approach and is slower than the normal foreground index build process. The speed of the index build process depends on the size of the index. If the index size is bigger than the RAM of the system, the process takes more time than the foreground process. Building indexes can impact your database performance if the application includes create index operations and if no index is available for operational concerns. To avoid any performance issues, you can use the getIndexes method to ensure that your application checks for the indexes at the startup. You can also use an equivalent method for your driver and ensure it terminates an operation if the proper indexes do not exist. When building indexes, use separate application codes and designated maintenance windows. We will discuss how to create indexes on replica sets in the next screen. Typically, background index operations on the secondary replica set begin after the index building process completes in the primary. If the index build process is running in background on the primary, then same will happen on the secondary nodes as well. If you want to build large indexes on secondaries, you can build the index by restarting one secondary at a time in a standalone mode. After the index build is complete, restart as a member of the replica set. Allow it to catch up with the other members of the set, and then build the index on the next secondary. When all the secondaries have the new index, step down the primary, restart it as a standalone, and build the index on the former primary. To ensure that the secondary catch up with primary, the time taken to build the index on a secondary must be within an op log. To catch up with primary node, index creation on secondary nodes always happen in the foreground in the recovering mode. Instead of using the default name, you can specify a name for the index by using the command given on the screen. This will create an index on the item field whose name will be item_index for the customer_info collection. In the next screen, we will discuss how to remove indexes. You can use the following methods to remove indexes. Drop index method. This removes an index from a collection. db.collection.dropIndex method. This removes an index. For example, the first operation given on the screen removes an ascending index on the item field in the items collection. To remove all indexes barring the _ID index from a collection, use the second operation provided on the screen. In the next screen, we will discuss how to modify an index. To modify an index, first drop the index and then recreate it. Perform the following steps to modify an index. Step 1. Drop index. Execute the first query given on the screen to return a document showing the operation status. If the operation is successful, the OK field in the returned document will display numeric 1. Step 2. Recreate the index without the unique constraint. Execute the second query given on the screen to return a document showing the status of the results. For example, if the operation is successful, the returned document shows number indexes after as greater than number indexes before by 1. In the next screen, we will view a demo on how to drop an index. This demo will show you the steps to drop indexes for a collection. In this demo, you will learn how to drop indexes from a collection. To drop an index from a collection, execute the command as shown on the screen. This command will drop a compound index created on the item and available fields of the items collection. The output displayed on the screen shows OK as 1. This indicates that the index is dropped. The N index was indicates the number of indexes that exists on the selected collection. To drop an index that was created only on the item field, execute the command given on the screen. Additionally, to drop all the non-ID indexes created on the collection, execute the command shown on the screen. In the result displayed, notice that the message field indicates that all the non-ID fields are dropped for the collection. This concludes the demo on how to drop indexes from a collection. In addition to modifying indexes, you can also rebuild them. To rebuild all indexes of a collection, use the db.collection.reindex method. This will drop all indexes including _ID and rebuild all indexes in a single operation. The operation takes the form db.items.reindex. To view the indexing process status, type the db.currentOperation command in the Mongo shell. The message field will show the percentage of the build completion. To abort an ongoing index build process, use the db.kill operation method in the Mongo shell. For index builds, the db.kill operation may occur after most of the index build operation has completed. Note that a replicated index build on the secondary replica set cannot be aborted. In the next screen, we will discuss listing indexes. You can list all indexes of a collection and a database. You can get a list of all indexes of a collection by using the db.collection.getIndexes or a similar method for your drivers. For example, to view all indexes on the items collection, use the db.items.getIndexes method. To list all indexes of collections, you can use the operation in the Mongo shell as shown on the screen. In the next screen, we will view a demo on retrieving indexes for a collection and database. This demo will show you the steps to retrieve indexes for a collection and a whole database function. In this demo, you will learn how to retrieve indexes for a collection and a whole database function. To retrieve all indexes for items collection, execute the query given on the screen. The result returns 5 documents. Notice that 3 indexes on the items collection are displayed. The first index is the default index created on the _ID field. The second and the third indexes are the ones which you have created. Similarly, to retrieve all indexes for items collection, execute the query given on the screen. To retrieve the list of all the indexes for all the collections in the database, execute the command given on the screen. The result displays the list of all the indexes in the collection and the database. This concludes the demo on retrieving indexes for a collection and a database. Typically, query performance indicates an index usage. MongoDB provides a number of tools to study query operations and observe index use for your database. The explain method can be used to print information about query execution. The explain method returns a document that explains the process and indexes used to return a query. This helps optimize a query. Using the db.collection.explain or the cursor.explain method helps measure index usages. In the next screen, we will view a demo on using Mongo shell methods to monitor index usage. This demo will show you the steps to use different Mongo shell methods to monitor the usage of indexes. In this demo, you will learn how to use different Mongo shell methods to monitor the usage of indexes. To view different methods, commands provided by MongoDB, first type help in the Mongo shell. The result displays a list of commands supported by MongoDB, such as show database, show collections, show profile, show users, show logs, and so on. It also displays helpful administrative methods, such as help admin, help connect, help miscellaneous, and so on. To view other methods available for the collection, type the command db.item.help as shown in the screen. Note that item is the name of the collection. You can use any collection present in your MongoDB database. The output displays the list of methods supported by MongoDB, such as find, count, convert to capped, data size, and so on. MongoDB provides many utilities methods to manage indexes, such as drop index, create index, total index size, storage size, and total size. To find out the store size of your collection and indexes, use the storage size and total index size methods as shown on the screen. The output displays the different metrics for the collection for monitoring and managing the collection. To rebuild the indexes, use the reindex method as shown on the screen. Next, to view the different metrics for the collection, type in the database. Use the command as shown on the screen. The output displays the different metrics for each collection in the database. This concludes the demo on using different Mongo shell methods to monitor the usage of indexes. In case you want to force MongoDB to use particular indexes for querying documents, then you need to specify the index with the hint method. The hint method can be appended in the find method as well. Consider the example given on the screen. This command queries a document whose item field value is book, and available field is true. Here, MongoDB's query planner is directed to use the index created on the item field. To view the execution statistics for a specific index, use the explain method in the find command. For example, consider the queries given on the screen. If you want to prevent MongoDB from using any index, specify the natural operator to the hint method. For example, use the following query given on the screen. In the next screen, we will view a demo on using operators, explain, hint, and natural to create an index. This demo will show you the steps to use the operators explain, hint, and natural to create an index. In this demo, you will learn how to use the operators explain, hint, and natural to create an index. To retrieve different query plans generated by MongoDB for a query using the explain method, execute the command given on the screen. The explain method displays different plans: winning plan, query plan, rejected plans, and bounds for indexes. You can force MongoDB to use a particular index by using the hint method while executing the find query. For the MongoDB query planner to use the index created on the item field, execute the command given on the screen. From the query plan displayed on the screen, you can see that MongoDB has used the index created on the item field provided in the hint method. You can add the natural operator to the hint method and prevent MongoDB from using any index. To do this, execute the command given on the screen. The output displayed does not list any index. Hence, it verifies that MongoDB has not used any index for retrieving the documents for this query. This concludes the demo on using the explain, hint, and natural operator for creating an index. MongoDB provides different metrics to report index use and operation. You can consider these metrics when analyzing index use for your database. These metrics are printed using the following commands. Server status prints two metrics, scanned and scan in order. Scanned displays the documents that MongoDB scans in the index to carry out the operation. If the number of scanned document is higher than the number of returned documents, this indicates that the database has scanned many objects to find the target object. In such cases, consider creating an index to improve this. Scan and order is a Boolean that is true when a query cannot use the order of documents in the index for returning sorted results. MongoDB must sort the documents after it receives the documents from a cursor. If scan and order is false, MongoDB can use the order of the documents in an index to return the sorted results. Collection statistics prints the two metrics: total index size, which returns index size in bytes. Index sizes explains the size of the data allocated for an index. Database statistics has the following two metrics. dbstats.indexes contains a count of the total number of indexes across all collections in the database. dbstats.indexsize, the total size in bytes of all indexes created on this database. In the next screen, we will discuss geospatial index. With the increased usage of handheld devices, geospatial queries are becoming increasingly frequent for finding the nearest data points for a given location. MongoDB provides geospatial indexes for coordinating such queries. Suppose you want to find the nearest coffee shop from your current location. You need to create a special index to efficiently perform such queries because it needs to search in 2 dimensions, longitude and latitude. A geospatial index is created using the createIndex function. It passes 2D or 2D sphere as a value instead of 1 or -1. To query geospatial data, you first need to create geospatial index. In the index specification document for the db.collection.createIndex method, as shown on the screen, specify the location as the index key and specify the string literal 2D sphere as the value. A compound index can include a 2D sphere index key in combination with non-geospatial index keys. In the next screen, we will view a demo on how to create geospatial indexes. This demo will show you the steps to create geospatial indexes in MongoDB. In this demo, you will learn how to create geospatial indexes in MongoDB. Let us first insert a document into the collection Places, which has a field called Location that contains geospatial data, latitude and longitude. The Places collection has 2 more fields called Name and Category. To perform the insert function, execute the command given on the screen. To store a couple of more documents in the Places collection, execute the command given on the screen. To view all the inserted documents in the Places collection, execute the command as shown on the screen. Notice that every document in the collection has a location field type point containing geospatial data. MongoDB enables you to efficiently query geospatial data by creating a geospatial index. To create a compound geospatial index on the location, category, and name field, execute the command shown on the screen. Note that the index on the location is of type 2D sphere. The result shows that the index is created. You can also create single field indexes on the geospatial field. To do so, execute the command shown on the screen. MongoDB does not force you to keep the geospatial field as the first field in the compound index. The command shown on the screen indicates that category is the first field instead of location while creating another compound geospatial index. To view all the geospatial indexes created on the Places collection, execute the command shown on the screen. Notice that 3 out of 4 are geospatial indexes. This concludes the demo on creating geospatial indexes in MongoDB. The geospatial query operators in MongoDB lets you perform the following queries. Inclusion queries return the locations included within a specified polygon. The inclusion queries use the operator GeoWithin. The 2D and 2D sphere indexes support this query. Although MongoDB does not require any index to perform an inclusion query, they can enhance the query performance. Intersection queries return locations intersecting with a specified geometry. These queries use the GeoIntersects operator and return the data on a spherical surface. Only 2D sphere indexes support intersection. Proximity queries return various points closer to a specified point. Proximity queries use the near operator that requires a 2D or 2D sphere index. In the next screen, we will view a demo on using geospatial indexes in a query. This demo will show you the steps to use geospatial indexes in the Find query of MongoDB. In this demo, you will learn how to use geospatial indexes in the Find query of MongoDB. You want to find out all those places located within 10 radian of your current location, whose latitude and longitude coordinates are minus 74.40 and 40.0. For this, use the Find query in the command given on the screen. This query will display all those points which are within a circle of given center and radius. The results shows all the data points which are near to minus 74.40 and 40.0. Next, you want to find the data points in the box shape of the coordinates minus 174.0 at the bottom left corner and by 10 and 100 at the top right corner. For this, execute the command given on the screen. The result displays all the data points which are within the specified box. To find all the data points within a polygon whose vertices are 0, 0, minus 90.45.0, minus 150.0, and 0, 0, execute the query given on the screen. Notice that the result displays the data points within the polygon. This concludes the demo on creating geospatial indexes in MongoDB. The GeoWithin operator is used to query location data found within a GeoJSON polygon. To get a response, the location data needs to be stored in the GeoJSON format. You can use the syntax given on the screen to use the GeoWith operator. The example given on the screen selects all points and shapes that exist entirely within a GeoJSON polygon. We will discuss proximity queries in MongoDB in the next screen. Proximity queries return the points closest to the specified point. These queries sort the results by its proximity to the specified point. You need to create a 2D sphere index in order to perform a proximity query on the GeoJSON data points. To query the data, you can either use the near or geonear operator. The first syntax given on the screen is an example of the near operator. The geonear command uses the second syntax given on the screen. This command offers additional options and returns further information than the near operator. In the next screen, we will discuss aggregation. Operations that process data sets and return calculated results are called aggregations. MongoDB provides data aggregations that examine data sets and perform calculations on them. Aggregation is run on the MongoDB instance to simplify application codes and limit resource requirements. Similar to queries, aggregation operations in MongoDB use collections of documents as an input and return results in the form of one or more documents. The aggregation framework in MongoDB is based on data processing pipelines. Documents pass through multi-stage pipelines and gets transformed into an aggregated result. The most basic pipeline stage in the aggregation framework provides filters that function like queries. It also provides document transformations that modify the output document. The pipeline operations group and sort documents by defined field or fields. In addition, they perform aggregation on arrays. Pipeline stages can use operators to perform tasks, such as calculate the average or concatenate a string. The pipeline uses native operations within MongoDB to allow efficient data aggregation, and is the favored method for data aggregation. In the next screen, we will continue our discussion on data aggregation. With the help of the aggregate function, you can perform complex aggregation operations, such as finding out the total transaction amount for each customer. In the diagram shown on the screen, orders is the collection that has three fields: customer underscore ID, amount, and status. In the match stage, you will filter out those documents in which status field value is A. In the group stage, you will aggregate the amount field for each customer underscore ID. In the next screen, we will discuss pipeline operators and indexes. The aggregate command in MongoDB functions on a single collection and logically passes the collection through the aggregation pipeline. You can optimize the operation and avoid scanning the entire collection by using the match, limit, and skip stages. You may require only a subset of data from a collection to perform an aggregation operation. Therefore, use the match, limit, and skip stages to filter the documents. When placed at the beginning of a pipeline, the match operation scans and selects only the matching documents in a collection. Placing a match before sort in the pipeline stage is equivalent to using a query in which the sorting function is performed before looking into the indexes. Therefore, it is recommended to use match operators at the beginning of the pipeline. In the next screen, we will discuss aggregate pipeline stages. Typically, pipeline stages appear in an array. Documents are passed through the pipeline stages in a proper order, one after the other. Barring out and geo-near, all stages of the pipeline can appear multiple times. The db.collection.aggregate method provides access to the aggregation pipeline and returns a cursor and result sets of any size. The various pipeline stages are as follows. Project. This stage adds new fields or removes existing fields and thus restructure each document in the stream. This stage returns one output document for each input document provided. Match. It filters the document stream and allows only matching documents to pass into the next stage without any modification. Match uses the standard MongoDB queries. For each input document, it returns either one output document if there is a match, or 0 documents when there is no match. Group. This stage groups documents based on the specified identifier expression and applies logic known as accumulator expression to compute the output document. Sort. This stage rearranges the order of the document using specified sort keys. The documents remain unaltered even though the order changes. This stage provides one output document for each input document. We will continue our discussion on aggregate pipeline stages in the next screen. Some more pipeline stages include the following. Skip. This stage skips the first n documents where n is the specified skip number. It passes the remaining documents without any modifications to the pipeline. For each input document, it returns either 0 documents for the first n documents or 1 document. Limit. It passes the first n number of documents without any modifications to the pipeline. For each input document, this stage returns either 1 document for the first n documents or 0 documents after the first n documents. Unwind. It deconstructs an array field in the input documents to return a document for each element. Each output document replaces the array with an element value. For each input document, it returns n documents where n is the number of array elements and can be 0 for an empty array. In the next screen, we will discuss pipeline operators and indexes. The aggregation operation given on the screen returns all states with total population greater than 10 million. This example depicts that the aggregation pipeline contains the group stage followed by the match stage. In this operation, the group stage does 3 things. 1. Groups the documents of the zip code collection under the state field. 2. Calculates the total population field for each state, and 3. Returns an output document for each unique state. The new per-state documents contains two fields, the _ID field and the total population field. Here, in this command, the aggregate pipeline is used. The sort stage orders those documents, and group stage applies the sum operation on the amount fields of those documents. The second aggregation operation shown on the screen returns usernames sorted by the month of their joining. This kind of aggregation could help generate membership renewal notices. In the next screen, we will view a demo on using the aggregate pipeline framework. This demo will show you the steps to use the aggregate pipeline framework in MongoDB. In this demo, you will learn how to use the aggregate pipeline framework in MongoDB. Suppose you want to retrieve all the transactions whose values are greater than 71,357,730. To achieve this, use the aggregate function as shown on the screen. The aggregate pipeline and the match stage is used for retrieving the documents whose transaction values are greater than the specified amount. The sort stage sorts the orders of the documents, and the group stage applies the sum operation on the amount fields of those documents. The result displays the number of retrieved documents matching the specified criteria. This concludes the demo on using the aggregate pipeline framework in MongoDB. MapReduce is a data processing model used for aggregation. To perform MapReduce operations, MongoDB provides the MapReduce database command. A MapReduce operation consists of two phases. In the map stage, documents are processed and one or more objects are produced for each input document. In the reduce stage, the outputs of the map operation are combined. Optionally, there can be an additional stage to make final modifications to the result. Similar to other aggregation operations, MapReduce can define a query condition to select the input documents and sort and limit the results. We will continue our discussion on MapReduce in the next screen. The MapReduce function in MongoDB can be written as JavaScript codes. The MapReduce operations accept set of documents from a collection as inputs, performs sort and limit functions, and then start the map stage. At the end of a MapReduce operation, the result is generated as documents which can be saved in the collection. Typically, the MapReduce operations in MongoDB associate values to a key by using the custom JavaScript functions. If a key contains more than one mapped value, then this operation converts them into a single object, such as an array. The use of custom JavaScript functions make the MapReduce operations flexible. For example, the map function can generate more than one key and value when processing documents. Additionally, the MapReduce operations use the custom JavaScript function to alter the results at the conclusion of the map, and reduce operations may perform further calculations. We will continue with MapReduce in the next screen. If a collection is sharded, then you can use MapReduce to perform many complex aggregation operations. The diagram on the screen depicts the orders in the collection having three fields: customer_ID, amount, and status. If you want to find out the sum of the total amount for each customer, then use the MapReduce framework. In the map stage, customer_ID and amount will be generated as the key. Value will be further processed by the reduce stage, in which customer_ID and array of amount will be passed as input to each reducer. The reducer then finds out the total of amount and generate customer_ID as key and order_totals as value. In the next screen, we will view a demo on using the MapReduce function. This demo will show you the steps to use the MapReduce function in MongoDB. In this demo, you will learn how to use the MapReduce function in MongoDB. Let us first define the map and reduce methods before using them in the MapReduce framework. Execute the commands shown on the screen. In these commands, the map method generates the customer_name field as the key and the amount as the value, while the reduce function takes array of amounts for that customer_name and populates the aggregate of the amounts. Next, execute the MapReduce command given on the screen. This command uses three parameters: the map method, reduce method, and the output collection name. The output of this command is stored in a new collection called MapReduce_result. Notice that the output shows that the map stage has processed 1 million documents, while reduce stage has processed 70,000 documents to generate 7 documents in the MapReduce_result collection. To confirm that the new collection is created, execute the Show Tables command. To view all the documents in the MapReduce_result collection, execute the command given on the screen. The result shows that 7 documents in this collection are returned. Each document contains the ID and value fields. The value fields hold total transaction amount of the respective customers. This concludes the demo on using MapReduce in MongoDB. Aggregations are operations that manipulate data and return a computed result based on the input document and a specific procedure. MongoDB performs aggregation operations on datasets. Aggregation operations have limited scope compared to the aggregation pipeline and MapReduce functions. Aggregation operations provide the following semantics for common data processing options. Count. MongoDB returns all of the documents matching a query. The count command, along with the two methods, count and cursor.count, provide access to total counts in the Mongo shell. The db.customer_info.count method command, as shown in the screen, helps count all documents in the customer_info collection. Distinct. The distinct operation searches for documents matching a query and returns all unique values for a field in the matched document. The distinct command and db.collection.distinct method execute this operation in the Mongo shell. The syntax given on the screen is an example of a distinct operation. In the next screen, we will view a demo on how to use the distinct and count methods. This demo will show you the steps to use the distinct and count methods in MongoDB. In this demo, you will learn how to use distinct and count methods in MongoDB. Using distinct method in MongoDB, you can count the number of documents having unique value for the given field. To get some distinct customer name out of millions of users, execute the query given on the screen. Notice that the result returns 7 unique customer names. To view the number of documents in the customer_info collection, use the count method as shown on the screen. You can also use the count method to count documents having fields with specified value. For example, to view the number of documents that contain the customer name field value John, execute the query given on the screen. The result shows that there are 143,115 documents which contain the customer_name as John. This concludes the demo on using distinct and count methods in MongoDB. Group operation accepts sets of documents as input which matches the given query. Apply the operation and then returns array of documents with the computed results. Note that group does not support sharded collection data. In addition, the results of the group operation must not exceed 16 megabytes. The group operation shown on the screen groups documents by the field A, where A is less than 3, and sums the field count for each group. In the next screen, we will view a demo on how to use the group function in MongoDB. This demo will show you the steps to use the group function in MongoDB. In this demo, you will learn how to use the group function in MongoDB. You want to find out the sum total of all the transactions of the customer named John. For this, use the group function as shown on the screen. The key specifies the field name and condition specifies the selection criteria for selecting the documents. Finally, the logic written in the reduce function gets applied on the selected documents to generate the output. The result displays customer_name as John and amount as 71,581,278. This concludes the demo on using the group method in MongoDB. Here is a quick recap of what was covered in this lesson. Indexes are data structures that store data set in easily traversable form. Indexes help execute queries efficiently without performing a collection scan. MongoDB supports the following indexes: single field, compound, multi-key, geospatial, text, and hashes. For fast query operation, the system RAM must be able to accommodate index sizes. You can create, modify, rebuild, and drop indexes. The geospatial indexes help query geographic location by specifying a specific point. The aggregation operations manipulate data and return a computed result based on the input and a specific procedure. Aggregation functions in MongoDB help query operations such as calculating total sum spent by a customer on online shopping site. This concludes the lesson, Indexing and Aggregation in MongoDB. In the next lesson, we will discuss replication and sharding in MongoDB. Lesson 5 of the MongoDB Developer course offered by Simplilearn. This lesson will explain how the replication and sharding features in MongoDB help in scaling read and write operations. Let us explore the objectives of this lesson in the next screen. After completing this lesson, you will be able to explain how the replication process works, explain the master-slave replication, replica sets, and replica set members, explain automatic failover, explain write concern, read preference, and tag sets. Describe the replica set deployment architecture. Explain how to enable sharding for database and collections. List different types of sharding keys and explain when to use sharding and how to deploy a sharded cluster. We will begin with a brief introduction to replication in the next screen. The primary task of a MongoDB administrator is to set up replication and ensure that it is functioning correctly. The replication functionality is recommended for use in the production setting. Replication increases data availability by creating redundancy. Replication stores multiple copies of data across different databases in multiple locations, and thus protects data when the database suffers any loss. In addition, it helps you manage data in the event of hardware failure and any kind of service interruptions. Having multiple copies of data stored at various servers across various locales, you can perform tasks such as disaster recovery, backup, or reporting with ease. You can also use replication to enhance read operations. Typically, clients send read and write operations to different servers. You can store copies of these operations in different data centers to increase the locality and availability of data for distributed applications. In the next screen, we will discuss the master-slave replication. The master-slave replication is the oldest mode of replication that MongoDB supports. In the earlier versions of MongoDB, the master-slave replication was used for failover, backup, and read scaling. However, in the new versions, it is replaced by replica sets for most use cases. Although MongoDB still supports the master-slave replication, replica sets are recommended for new production deployments to replicate data in a cluster. In the next screen, we will discuss replica sets in MongoDB. A replica set consists of a group of MongoDB instances that host the same data set. In a replica set, the primary MongoDB receives all write operations, and the secondary MongoDB replicates the operations from the primary, and thus both have the same data set. The primary node receives write operations from clients. A replica set can have only one primary, and therefore only one member of the replica set can receive write operations. A replica set provides strict consistency for all read operations from the primary. The primary logs any changes or updates to its datasets in its oplog. The secondaries also replicate the oplog of the primary and apply all the operations to their datasets. When the primary becomes unavailable, the replica set nominates a secondary as the primary. By default, clients read data from the primary. However, they can also specify read preferences and request read operations to send to the secondaries. Reads from secondaries may return data that does not reflect the state of the primary. The diagram given on the screen depicts that the primary member of the replica set receives all the read and write requests by default. However, read requests can be directly sent to the secondary member of the replica set too. We will continue our discussion on replica sets in MongoDB in the next screen. You can choose to add an extra MongoDB instance to a replica set to act as an arbiter. Note that arbiters do not maintain a data set. They only elect the primary. An arbiter is the node that just participates in the election to select the primary node, and it does not store any data and hence does not require a dedicated hardware. Secondary members in a replica set asynchronously apply operations from the primary. By applying operations after the primary, replica sets can function without any secondary members. As a result, all secondary members may not return the updated data to clients. A primary can convert to a secondary or vice versa. However, an arbiter will remain unchanged. We will discuss how a replica set handles automatic failover in the next screen. When the primary node of a replica set stops communicating with other members for more than 10 seconds or fails, the replica set selects another member as the new primary. The selection of the new primary happens through an election process, and whichever secondary node gets majority of the votes becomes the primary. A replica set supports application needs in various ways. For example, you may deploy a replica set in multiple data centers, or manipulate the primary election by adjusting the priority of members. In addition, replica sets support dedicated members for functions such as reporting, disaster recovery, or backup. In the next screen, we will discuss replica set members. In addition to the primary and secondaries, a replica set can also have an arbiter. Unlike secondaries, arbiters do not replicate or store data. However, arbiters play a crucial role in selecting a secondary to take the place of the primary when the primary becomes unavailable. Therefore, a typical replica set contains a primary, a secondary, and an arbiter. Typically, most of the replica set deployments keep 3 members that store data, 1 primary and 2 secondaries. A replica set in MongoDB version 3.0 can have up to 50 members, but only 7 members are capable of voting. In the previous versions of MongoDB, replica sets could have a maximum of 12 members. In the next screen, we will discuss Priority 0 replica set members. A Priority 0 member in a replica set is a secondary member that cannot become the primary. These members can act as normal secondaries, but cannot trigger any election. A Priority 0 member performs functions such as maintaining data set copies, accepting and performing read operations, and electing the primary. By configuring a Priority 0 member, you can prevent secondaries from becoming the primary. This is particularly useful in multi-data center deployments. In a replica set containing 3 members, one data center hosts both the primary and a secondary, and the second data center hosts one Priority 0 member. Typically, a Priority 0 member acts as a backup. For example, in some replica sets, a new member may not be able to add immediately. The backup or standby member stores the updated data and can immediately replace an unavailable member. In the next screen, we will discuss hidden replica set members. Hidden members of a replica set are invisible to the client applications. They store a copy of the primary's data and are good for workloads with different usage patterns from the other members in the replica set. Although the hidden replica set members are Priority 0 members and can never replace the primary, they may elect the primary. In the 5-member replica set shown on the screen, all the 4 secondary members contain the primary data set copies and one hidden secondary member. Typically, the clients of read operations do not distribute appropriate read rights to the hidden members. Therefore, the hidden members receive only the basic replication traffic. You can utilize the hidden members for dedicated functions like reporting and backups. In a sharded cluster, MongoS do not interact with the hidden replica set members. In the next screen, we will discuss delayed replica set members. Delayed replica set members are those secondaries that copy data from the primary node's oplog file after a certain interval or delay. Delayed replica set members store their data set copies. However, they reflect a previous version or a delayed state of the set. For example, if the data shown in the primary is for 10 a.m., then the delayed member will show data for 9 a.m. Delayed members perform a roll backup or run a historical snapshot of the data set. Therefore, they help you manage various human errors and recover from errors, such as unsuccessful application upgrade and dropped databases and collections. A delayed member must be a Priority 0 member, must be hidden and not visible to applications, and must participate in electing the primary. In the next screen, we will discuss the configuration settings of delayed replica set members. You can configure a delayed secondary member with the following settings: priority value 0, hidden value true, and slave delay value number of seconds to delay. You can set a 1-hour delay on a secondary member currently at the index 0 in the members array. To set the delay, issue the sequence of operations given on the screen in a Mongo shell connected to the primary. After a replica set reconfigures, the delayed secondary member cannot replace the primary and is hidden from applications. The slave delay value delays both replication and the member's oplog by 3,600 seconds or 1 hour. In the next screen, we will view a demo on how to start a replica set. This demo will show the steps to start a replica set in MongoDB. In this demo, you will learn how to start a replica set in MongoDB. We will start 3 MongoDB instances. These instances will run on the same machine, and each one will use a separate directory. First, create 3 directories in the C:\data folder. Let us start the first MongoDB instance. Next, start the second MongoDB instance. Finally, start the third MongoDB instance. Now, by connecting to one of the MongoDB server. In the Mongo shell, type the command shown on the screen to connect all the 3 MongoDB instances to the replica set RSO. After creating the replica set config object, initialize the replica set by calling the initiate method on the RS object as shown on the screen. Next, check the configuration of the replica set by executing the rs.conf method. The output displayed on the screen provides information regarding all the members of the replica set, such as host name, priority, and votes. It also shows whether the members are arbiter only or hidden. This concludes the demo on creating a replica set in MongoDB. The write concern provides an assurance of the success of a write operation. The strength or weakness of a write concern determines the level of assurance. For operations having weak concerns, such as updates, inserts, and deletes, the write operations return a quick result. Write operations having weak write concerns may fail. When stronger write concerns are used in an operation, clients wait after sending the operation for MongoDB to confirm their success. MongoDB provides different levels of write concerns to address the varied application needs. Clients may manage write concerns to ensure that the critical operations are successfully carried out on the MongoDB deployment. For less critical operations, clients can manage the write concern to ensure faster performance rather than ensure persistence to the entire deployment. Typically, regardless of the write concern level or journaling configuration, MongoDB allows clients to read the inserted or modified documents before committing the modifications to the disk. As a result, if an application has multiple readers and writers, MongoDB allows a reader to read the data of another writer even when the data is still not committed to the journal. We will continue our discussion on write concern in the next screen. MongoDB modifies each document of a collection separately. For multi-document operations, MongoDB does not provide any multi-document transactions or isolation. When a standalone MongoDB returns a successful journaled write concern, the data is stored to the disk and becomes available after MongoDB restarts. Write operations in a replica set can become durable only after a write data gets replicated and committed to the journal on majority of the voting members of a replica set. MongoDB periodically commits data to the journal as defined by the commit interval millisecond parameter. In the next screen, we will discuss write concern levels. MongoDB has two levels of conceptual write concern, unacknowledged and acknowledged. In an unacknowledged write concern, MongoDB does not acknowledge the received write operations or ignores it. This is similar to ignored errors. However, the driver is capable of receiving and handling network errors whenever possible. The driver's ability to detect and handle network errors depends on the networking configuration of the system. In an acknowledged write concern, the MongoDB confirms the receipt of the write operation. It also confirms that the changes to the in-memory data view are applied. An acknowledged write concern can detect network, duplicate key, and other errors. By default, MongoDB uses the acknowledged write concern in the driver. The Mongo shell includes the write concern in the write methods and provides the default write concern whether it runs interactively or in a script. An acknowledged write concern does not confirm that the write operation has persisted to the disk system. Note that journaling must be enabled to use a write concern. In the next screen, we will discuss the write concern for a replica set. Replica sets have additional considerations for write concerns. Typically, the default write concerns in a replica set require acknowledgement only from the primary member. A write concern acknowledged by a replica set ensures that the write operation spreads to the other members of the set. The default write concern confirms write operations only for the primary. However, you can choose to override this write concern to check write operations on some replica set members. You can override the default write concern by specifying a write concern for each write operation. For example, the method given on the screen contains a write concern that specifies that the method should return a response only after the write operation is spread to the primary and minimum one secondary, or the method times out after 5 seconds. In the next screen, we will discuss how to modify default write concerns. You can modify a default write concern by changing the Get Last Error Default setting in the replica set configuration. This write operation will complete most of the voting members before returning the result. The sequence of commands given on the screen creates a configuration that waits for the write operation to complete. Additionally, you can include a timeout threshold for a write concern to prevent blocking write operations. For example, a write concern must be acknowledged by 4 members of a replica set. However, only 3 members are available in the replica set. The operation blocks until all the 4 members are available. You can prevent the operation from blocking by adding a timeout. In the next screen, we will discuss read preferences. Read preferences define how MongoDB clients route read operations to replica set members. By default, a client directs its read operations to the primary. Therefore, reading from the primary member means that you have the latest version of a document. However, you can distribute reads among the secondary members to improve the read performance or reduce latency for applications that do not require the up-to-date data. The typical use cases for using non-primary read preferences are as follows: running systems operations that do not affect the front-end application, providing local reads for the geographically distributed applications, maintaining availability during a failover. You can use mongo.setReadPreference method to set a read preference. We will discuss the read preference modes in the next screen. The read preference modes supported in a replica set are as follows. Primary. This is the default read preference mode. All operations read from the current replica set are primary. Primary preferred. Operations are mostly read from the primary member. However, when the primary is unavailable, operations are read from a secondary member. Secondary. All operations are read from secondary members of the replica set. Secondary preferred. In most situations, operations are read from a secondary, but when a secondary member is unavailable, operations are read from the primary. Nearest. Operations are read from a member of the replica set with the least network latency, irrespective of the member's type. In the next screen, we will discuss blocking for replication. The getLastError command in MongoDB ensures how the up-to-date replication is done by using the optional W parameter. In the query shown on the screen, the getLastError command is run that blocks until at least n number of servers have replicated the last write operation. The query will return immediately if n is either not present or is less than 2. If n equals 2, the master will respond to the command only after one slave replicates the last operation. Note that the master is included in n. The master uses the synced-to information stored in local slaves to identify how up-to-date each slave is. When specifying W, the getLastError command takes an additional parameter, W timeout, a timeout in milliseconds. This allows the getLastError command to timeout and return an error before the last operation has replicated to n servers. However, by default, the command has no timeout. Blocking the replication significantly slows down write operations, particularly for large values of W. Setting W to 2 or 3 for important operations yields a good combination of efficiency and safety. In the next screen, we will discuss tag sets. Tag sets allow tagging target read operations to select the replica set members. Customized read preferences and write concerns assess tag sets differently. Typically, read preferences stress on the tag value when selecting a replica set member to read from. Write concerns, on the other hand, ignore the tag value when selecting a member. However, they confirm whether the value is unique. You can specify tag sets with the following read preference modes: primary preferred, secondary, secondary preferred, and nearest. Remember, tags and the primary mode are not compatible, and, in general, tags apply only when selecting a secondary member of a read operation. However, tags are compatible with the nearest mode. When combined together, the nearest mode selects the matching member, primary or secondary, with the lowest network latency. Typically, all interfaces use the same member selection logic to choose the member to direct read operations, and base the choice on the read preference mode and tag sets. In the next screen, we will discuss how to configure tag sets for replica sets. Using tag sets, you can customize write concerns and read preferences in a replica set. MongoDB stores tag sets in the replica set configuration object, which is the document returned by rs.conf in the members.tags embedded document. When using either write concern or read scaling, you may want to have some control over which secondaries receive writes or reads. For example, you have deployed a 5-node replica set across 2 data centers, New York and London. New York is the primary data center that contains 3 nodes. The secondary data center, London, contains 2. Suppose you want to use a write concern to block until a certain write is replicated to at least 1 node in the London data center. You cannot use a W value of majority because this will translate into a value of 3. And the most likely scenario is that the 3 nodes in New York will acknowledge first. Replica set tagging resolves such problems by allowing you to define special write concern modes that target the replica set members with defined tags. To see how this works, you first need to learn how to tag a replica set member. In the config document, each member can have a key called tags pointing to an object containing key value pairs. You can add tag sets to the members of a replica set with the following sequence of commands in the Mongo shell as given on the screen. Modes can be defined as a document with 1 or more keys in the getLastErrorModes command. Here, in this command, you have defined a mode containing 2 keys, DC and rack New York, whose values are integers too. These integers indicate that the number of the tagged value must be satisfied in order to complete the getLastError command. In the next screen, we will discuss replica set deployment. A replica set architecture impacts the set's capability. In a standard replica set for a production system, a 3-member replica set is deployed. These sets provide redundancy and fault tolerance, avoid complexity, but let your application requirements define an architecture. Use the following deployment strategies for a replica set. Deploy an odd number of members. For electing the primary member, you need an odd number of members in a replica set. Add an arbiter in case a replica set has even number of members. Consider fault tolerance. Fault tolerance for a replica set is the number of members that can become unavailable and still leave enough members in the set to elect the primary. A replica set cannot accept any write operation if the primary member is not available. Remember that adding a new member to a replica set does not always increase its fault tolerance capability. However, the additional members added in a replica set can provide support for some dedicated functions, such as backups or reporting. Use hidden and delayed members. Add hidden or delayed members to support dedicated functions such as backup or reporting. Load balance on read-heavy deployments. In deployments with high read traffic, to improve read performance, distribute reads to secondary members. As your deployment grows, add or move members to alternate data centers and improve redundancy and availability. However, ensure that the main facility is able to elect the primary. In the next screen, we will continue with the replica set deployment strategy. Some more replica set deployment strategies are given below. Add capacity ahead of demand. You must be able to add a new member to an existing replica set to meet the increased data demands. Add new members before new demands arise. Distribute members geographically. For data safety in case of any failure, keep at least one member in an alternate data center. Also, set the priorities of these members to 0 so that they do not become the primary. Keep a majority of members in one location. When replica set members are distributed across multiple locations, network partition may hinder the communication between the data centers and affect data replication. When electing the primary, all the members must be able to see each other to create a majority. To enable the replica set members create a majority and elect the primary, ensure that majority of the members are in one location. Use replica set tag sets. This ensures that all operations are replicated at specific data centers. Using tag sets helps to route read operations to specific computers. Use journaling to protect against power failures. To avoid the data loss problem, use journaling so that data can be safely written on a disk in case of shutdowns, power failure, and other unexpected failures. In the next screen, we will discuss replica set deployment patterns. The common deployment patterns for a replica set are as follows. 3-member replica sets. This is the minimum recommended architecture for a replica set. Replica sets with 4 or more members. This set provides greater redundancy and supports greater distribution of read operations and dedicated functionality. Geographically distributed replica sets. These include members in multiple locations to protect data against facility-specific failures, such as power outages. In the next screen, we will discuss the oplog file. The record of operations maintained by the master server is called the operation log or oplog. The oplog is stored in a database called local in the oplog.main collection. Each oplog document denotes a single operation performed on the master server and contains the following keys. Timestamp or TS for the operation. It is an internal function used to track operations. It contains a 4-byte timestamp and a 4-byte incrementing counter. Op. This is the type of operation performed as a 1-byte code. For example, I for an insert. Namespace or NS is the collection name where the operation is performed. O. This key is used to document further specifying the operation to perform. For an insert, this would be the document to insert. The oplog stores only those operations that change the state of the database. The oplog is intended only as a mechanism for keeping the data on slaves in sync with the master. The oplog files do not exactly store the operations that are performed on the master. Rather, the operation gets transformed and then is stored into the oplog file. In the next screen, we will discuss replication state and local database. MongoDB maintains a local database called local to keep the information about the replication state and the list of master and slaves. The content of this database does not get replicated and remains local to the master and slaves. This list is stored in the slaves collection. Slaves store the replication information in the local database. The unique slave identifier gets saved in the Me collection, and the list of masters gets saved in Sources collection. The master and slave both use the timestamp stored in the synced-to command to understand how up-to-date a slave is. A slave uses synced-to to query the op log for new operations and find out if any operation is out of sync. In the next screen, we will discuss replication administration. MongoDB inspects the replication status using some administrative helpers. To check the replication status, use the function given on the screen when MongoDB inspects the replication status using some administrative helpers. To check the replication status, use the function given on the screen when connected to the master. This function provides information on the oplog size and the date ranges of operations contained in the oplog. In the given example, the oplog size is 10 megabyte and can accommodate about 30 seconds of operations. In such a case, you should increase the size of the oplog. You can compute the log length by determining the time difference between the first and the last operation. In case the server has recently started, then the first logged operation will be relatively recent. Hence, the log length will be small, even though the oplog may have some free space available. The log length serves as a metric for servers that have been operational long enough for the oplog to roll over. You can also get some information when connected to the slave using the functions given on the screen. This function will populate a list of sources for a slave, each displaying information such as how far behind it is from the master. In the next screen, we will view a demo on how to check the status of a replica set. This demo will show the steps to check the status of a replica set in MongoDB. In this demo, you will learn how to view the metrics of a replica set in MongoDB. First, connect to one of the MongoDB server, which is a member of a replica set. To check the status of the replica set, execute the command given on the screen. The result shows information such as name, health, state, and state str for each of the member in the replica set. You can print general information such as oplog size, log length, oplog first event, and oplog last event by executing the command given on the screen. You can also view the general information about the slave by executing the command given on the screen. The result displayed on the screen provides information about synced-to, which indicates the last time when the oplog file of primary was synced. To allow read operations to be handled by slave members of the replica set, use the slave OK method. To return a document that describes the role of the MongoDB instance, execute the isMaster method. If the instance is a member of a replica set, then isMaster returns a subset of the replica set configuration and status, including whether or not the instance is the primary member of the replica set. This concludes the demo on checking the status of a replica set in MongoDB. Sharding is the process of distributing data across multiple servers for storage. MongoDB uses sharding to manage massive data growth. With an increase in data size, a single machine may not be able to store data or provide an acceptable read and write throughput. Sharding supports horizontal scaling and thus is capable of distributing data across multiple machines. Sharding allows you to add more servers to your database to support data growth and automatically balances data and load across various servers. Sharding provides additional write capacity by distributing the write load over a number of MongoDB instances. It splits the data set and distributes them across multiple databases, or shards. Each shard serves as an independent database, and together, shards make a single logical database. Sharding reduces the number of operations each shard handles, and as a cluster grows, each shard handles fewer operations and stores lesser data. As a result, a cluster can increase its capacity and input horizontally. For example, to insert data into a particular record, the application needs to access only the shard that holds the record. If a database has a 1 terabyte data set distributed amongst 4 shards, then each shard may hold only 256 gigabyte of data. If the database contains 40 shards, then each shard will hold only 25 gigabyte of data. In the next screen, we will discuss when sharding should be used. Typically, sharded clusters require a proper infrastructure setup. This increases the overall complexity of the deployment. Therefore, consider deploying sharded clusters only when there is an application or operational requirement. You must consider deploying a sharded cluster when your system shows the following characteristics. The data set outgrows the storage capacity of a single MongoDB instance. The size of the active working set exceeds the capacity of the maximum available RAM. A single MongoDB instance is unable to manage write operations. In the absence of these characteristics, sharding will not benefit your system. Rather, it will add complexity. Deploying sharding consumes time and resources. In case your database system has already surpassed its capacity, deploying sharding without impacting the application is not possible. Therefore, deploy sharding if you expect that the read and write operations are going to be increased in future. In the next screen, we will discuss what a shard is. A shard is a replica set, or a single MongoDB instance that holds the data subset used in a sharded cluster. Shards hold the entire data set for a cluster. Each shard is a replica set that provides redundancy and high availability for the data it holds. MongoDB shards data on a per-collection basis and lets you access the sharded data through MongoS instances. If you directly connect to a shard, you will be able to view only a fraction of the data contained in a cluster. Data is not organized in any particular order. In addition, MongoDB does not guarantee that any 2 contiguous data chunks will reside on any particular shard. Note that every database contains a primary shard that holds all the unsharded collections in that database. In the next screen, we will discuss a shard key. When deploying sharding, you need to choose a key from a collection and split the data using the key's value. This key is called a shard key that determines how to distribute the documents of a collection among the different shards in a cluster. The shard key is a field that exists in every document in the collection and can be an indexed or indexed compound field. MongoDB performs data partitions in a collection using the different ranges or chunks of shard key values. Each range or chunk defines a non-overlapping range of shard key values. MongoDB distributes chunks and their documents among the shards in a cluster. MongoDB also distributes documents according to the range of values in the shard key. In the next screen, we will discuss how to choose a shard key. To enhance and optimize the performance, functioning, and capability of your database, you need to choose the correct shard key. Choosing the appropriate shard key depends on two factors: the schema of your data and the way applications in your database query and perform write operations. In the next screen, we will discuss the characteristics of an ideal shard key. An ideal shard key must have the following characteristics. Must be easily divisible. An easily divisible shard key enables MongoDB to perform data distribution among shards. If shard keys contain limited number of possible values, then the chunks in shards cannot be split. For example, if a chunk or a range represents a single shard key value, then the chunk cannot be split even if it exceeds the recommended size. High degree of randomness. A shard key must possess a high degree of randomness. This ensures that a single shard distributes write operations among the cluster and does not become a bottleneck. Target a single shard. A shard key must target a single shard to enable the MongoS program to return most of the query operations directly from a single MongoD instance. In addition, the shard key should be the primary field in queries. Fields having a high degree of randomness cannot target operations to specific shards. Use a compound shard key. If an existing field in your collection is not the ideal key, compute a special purpose shard key or use a compound shard key. In the next screen, we will discuss range-based sharding. In range-based sharding, MongoDB divides datasets into different ranges based on the values of shard keys. Thus, it provides range-based partitioning. For example, consider a numeric shard key. If an imaginary number line goes from -infinity to +infinity, each shard key value falls at some point on that line. MongoDB partitions this line into chunks where each chunk can have a range of values. In range-based sharding, documents having close shard key values reside in the same chunk and shard. Range-based partitioning supports range queries because for a given range query of a shard key, the query router can easily find which shards contain those chunks. Data distribution in range-based partitioning can be uneven, which may negate some benefits of sharding. For example, if a shard key field size increases linearly, such as time, then all requests for a given time range will map to the same chunk and shard. In such cases, a small set of shards may receive most of the requests, and the system would fail to scale. In the next screen, we will discuss hash-based sharding. For hash-based partitioning, MongoDB first calculates the hash of a field's value, then creates chunks using those hashes. Unlike range-based partitioning, in hash-based partitioning, documents with close shard key values may not reside in the same chunk. This ensures that the collection in a cluster is randomly distributed. In hash-based partitioning, data is evenly distributed. Hashed key values randomly distribute data across chunks and shards. The random distribution of data across chunks using hash-based partitioning makes range query on the shard key ineffective, as data will be distributed to many shards rather than a few number of shards, as in the case of range-based partitioning. In the next screen, we will discuss the impact of shard key cluster operation. Some shard keys are capable of scaling write operations. Typically, a computed shard key that possesses randomness to some extent allows a cluster to scale write operations. For example, hash keys that include a cryptographic hash such as MD5 or SHA1 can scale write operations. However, random shard keys do not provide query isolation. To improve write scaling, MongoDB enables sharding a collection on a hashed index. MongoDB improves write scaling using two methods, querying and query isolation. Querying. A MongoS instance provides an interface to enable applications to interact with sharded clusters. When MongoS receives queries from client applications, it uses metadata from the config server and routes queries to the MongoD instances. MongoS makes querying operational in sharded environments. However, the shard key you select can impact the query performance. Query isolation. Query execution will be fast and efficient if MongoS can route to a single shard using a shard key and metadata stored from the config server. Queries that require routed to many shards will not be efficient, as they will have to wait for a response from all of those shards. If your query contains the first component of a compound shard key, then MongoS can route a query to a single or the minimum number of shards, which provides good performance. In the next screen, we will discuss production cluster architecture. Special MongoD instances, such as config servers, store metadata for a sharded cluster. Config servers provide consistency and reliability using a two-phase commit. Config servers do not run as replica sets and must be available to deploy a sharded cluster or to make changes to a cluster metadata. The production sharded cluster shown in the image on the screen has the following three config servers. Each config server must be on separate machines. A single sharded cluster must have an exclusive use of its config servers. If you have multiple sharded clusters, you will need to have a group of config servers for each cluster. Config database. Config servers store the metadata in the config databases. The MongoS instance caches this data and uses it to route the reads and writes to shards. MongoDB performs writes operations in the config server only in the following cases: to split the existing chunks and to migrate a chunk between shards. MongoDB reads data from the config server when a new MongoS starts for the first time or an existing MongoS restarts. After a chunk migration, the MongoS instances update themselves with the new cluster metadata. MongoDB also uses the config server to manage the distributed locks. In the next screen, we will discuss config server availability. When one or more config servers are unavailable, the metadata of the cluster becomes read-only. You can still read and write data from shards. However, chunk migrations occur only when all the three servers are available. If all three config servers are unavailable, you can still use the cluster provided the MongoS instances do not restart. If the MongoS instances are restarted before the config servers are available, the MongoS become unable to route reads and writes. Clusters are inoperable without the cluster metadata. Therefore, ensure that the config servers remain available and intact throughout. Query routers are the MongoS processes that interface with the client applications and direct queries to the appropriate shard or shards. All the queries from client applications are processed by the query router, and in the sharded cluster, it is recommended to use 3 query routers. In the next screen, we will discuss production cluster deployment. When deploying a production cluster, ensure data redundancy and systems availability. A production cluster must have the following components. Config servers. There are 3 config servers. Each of the config servers must be hosted on separate machines. Each single sharded cluster must have an exclusive use of its config servers. For multiple sharded clusters, you must have a group of config servers for each cluster. Shards. A production cluster must have 2 or more replica sets or shards. Query routers or MongoS. A production cluster must have 1 or more MongoS instances. The MongoS instances act as the routers for the cluster. Production cluster deployments typically have 1 MongoS instance on each application server. You may deploy more than 1 MongoS instances and also use a proxy or load balancer between the application and MongoS. When making these deployments, configure the load balancer to enable a connection from a single client reach the same MongoS. Cursors and other resources are specific to a single MongoS instance, and hence each client must interact with only 1 MongoS instance. In the next screen, we will discuss how to deploy a sharded cluster. To deploy a sharded cluster, perform the following sequence of tasks. Step 1. Start the config server database instances. Create data directories for each of the 3 config server instances. By default, a config server stores its data files in the /data/config-db directory. You can also choose an alternate location to store the data. To create a data directory, issue the command as shown on the screen. Step 2. Start the 3 config server instances. Start each config server by issuing a command using the syntax given on the screen. The default port for config servers is 27019. You can also specify a different port. The example given on the screen starts a config server using the default port and default data directory. Step 3. Start the MongoS instance. By default, a MongoS instance runs on the port 27017. To start a MongoS instance, issue a command using the syntax given on the screen. For example, to start a MongoS that connects to a config server instance running on the following hosts and on the default ports, issue the last command given on the screen. In the next screen, we will discuss how to add shards to a cluster. To add shards to a cluster, perform the following steps. Step 1. From a Mongo shell, connect to the MongoS instance and issue a command using the syntax given on the screen. If a MongoS is accessible at node1.example.net on the port 27017, issue the following command given on the screen. Step 2. Add each shard to the cluster using the addShard method on the shconsole method, as shown in the examples given on the screen. Next, issue the addShard method on the shconsole method separately for each shard. If a shard is a replica set, specify the name of the replica set and specify a member of the set. In production deployments, all shards should be replica sets. To add a shard for a replica set named RS1 with a member running on the port 27017 on MongoDB0.example.net, issue the following command given on the screen. To add a shard for a standalone MongoD on the port 27017 of MongoDB0.example.net, issue the following command given on the screen. In the next screen, we will view a demo on how to create a sharded cluster in MongoDB. This demo will show the steps to create a sharded cluster in MongoDB. In this demo, you will learn how to create a sharded cluster in MongoDB. Let us first start the 3 config server instances. In this demo, all the 3 instances will run on the same machine, and each one will use their own config directory. Before running these config servers, create the 3 directories as shown on the screen. Let us start the first config server instance. Next, start the second config server instance. Next, start the third config server instance. To start MongoDB, the query router that connects to the config server instance, run it by using the command shown on the screen. Next, to connect to MongoDB, execute the command shown on the screen. To view the list of commands available in the sharded cluster, type sh.help. To add the MongoDB process to the shard, execute the command given on the screen. You need to enable sharding at the database level. For this, execute the command given on the screen. To target particular collection for sharding, execute the command given on the screen. This concludes the demo on creating a sharded cluster in MongoDB. Before you start sharding a collection, first enable sharding for the database of the collection. When you enable sharding for a database, it does not redistribute data but allows sharding the collections in that database. MongoDB assigns a primary shard for that database where all the data is stored before sharding begins. To enable sharding, perform the following steps. Step 1. From a Mongo shell, connect to the MongoDB instance. Issue a command using the syntax given on the screen. Step 2. Issue the sh.enable sharding method. Specify the name of the database for which you want to enable sharding. Use the syntax given on the screen. Optionally, you can enable sharding for a database using the enable sharding command. For this, use the syntax given on the screen. In the next screen, we will discuss how to enable sharding for a collection. You can enable sharding on a per-collection basis. To enable sharding for a collection, perform the following steps. Step 1. Determine the shard key value. The selected shard key value impacts the efficiency of sharding. Step 2. If the collection already contains data, create an index on the shard key using the createIndex method. If the collection is empty, then MongoDB will create the index as part of the sh.shardCollection step. Step 3. To enable sharding for a collection, open the Mongo shell and issue the sh.shardCollection method. The method uses the syntax given on the screen. we will continue with our discussion on enabling sharding for a collection. To enable sharding for a collection, replace the string database.collection with the full namespace of your database. This string consists of the name of your database, a dot, and the full name of the collection. The shard key pattern represents your shard key, which you specify in the same form as you would an index key pattern. This example given on the screen shows sharding collections based on the partition key. In the next screen, we will discuss maintaining a balanced data distribution. When you add new data or new servers to a cluster, it may impact the data distribution balances within the cluster. For example, some shards may contain more chunks than another shard, or the chunk sizes may vary, and some can be significantly larger than other chunks. MongoDB uses two background processes, splitting and balancer, to ensure a balanced cluster. In the next screen, we will discuss how MongoDB uses splitting to ensure a balanced cluster. Splitting is a background process that checks the chunk sizes. When a chunk exceeds a specified size, MongoDB splits the chunk into two halves. MongoDB uses the insert and update functions to trigger a split. When creating splits, MongoDB does not perform any data migration or affect the shards. When you split, the chunk distribution in collections across the shards may be uneven. In such cases, the MongoS instances will redistribute the chunks across shards. In the next screen, we will discuss chunk size. In MongoDB, the default chunk size is 64 megabytes. You can alter a chunk size. However, this may impact the efficiency of the cluster. Smaller chunks enable an even distribution of data, but may result in frequent migrations. Larger chunks encourage fewer migrations and are more efficient from the networking perspective and in terms of internal overhead at the query routing layer. However, this may lead to an uneven distribution of data. The chunk size affects the maximum number of documents per chunk to migrate. If you have many deployments to make, you can use larger chunks. This will help avoid frequent and unnecessary migrations, although the data distribution will be uneven. When you split chunks, changing the chunk size affects with the following limitations. Automatic splitting occurs only during inserts or updates. When you reduce the chunk size, all chunks may take time to split to the new size. Once you split chunks, they cannot be undone. When you increase the chunk size, the existing chunks must grow through inserts or updates until they reach the new size. In the next screen, we will discuss special chunk types. Following are the special chunk types. Jumbo chunks. MongoDB does not migrate a chunk if its size is more than the specified size, or if the number of documents contained in the chunk exceeds the maximum number of documents per chunk to migrate. In such situations, MongoDB splits the chunk. If the chunk cannot be split, MongoDB labels the chunk as jumbo. This avoids repeated attempts to migrate the same chunk. Indivisible chunks. Sometimes chunks can grow beyond the specified size but cannot be split. For example, when a chunk represents a single shard key value. Invisible chunks are those chunks that cannot be broken by the split process. In the next screen, we will discuss shard balancing. MongoDB uses balancing to redistribute data within a sharded cluster. It is a background process that manages chunk migrations. The balancer can run from any query routers in a cluster. When the shard distribution in a cluster is uneven, the balancer migrates chunks from one shard to another to achieve a balance in chunk numbers per shard. For example, if the collection users have 100 chunks on shard 1 and 50 chunks on shard 2, the balancer will migrate 25 chunks from shard 1 to shard 2 so that each shard may have 75 chunks. Chunk migrations is a background operation that occurs between two shards, an origin and a destination. The origin shard sends the destination shard to all the current documents. The destination shard captures and applies all the changes made to the data during the migration process. It also updates the metadata regarding the location of the chunk on the config server. During the migration, if an error occurs, the balancer aborts the process and leaves the chunk unchanged in the origin shard. After the migration completes, MongoDB removes the chunk's data from the origin shard. Adding and removing shards from the cluster. Adding a new shard to a cluster may create an imbalance because the new shard has no chunks. Although MongoDB begins migrating data to the new shard immediately, it can take some time before the cluster maintains a balance in all the shards. Similarly, when a shard is being removed, the balancer migrates all the chunks from the shard to the other shards. After all the data is migrated and the metadata is updated, the shard can be safely removed. In the next screen, we will continue with our discussion on shard balancing. Chunk migrations carry bandwidth and workload overheads, which may impact the database performance. Shard balancing minimizes the impact by moving only one chunk at a time, starting a balancing round only when the difference between the greatest number of chunks for a sharded collection and the shard with the lowest number of chunks for that collection reaches the migration threshold. In some scenarios, you may want to disable the balancer temporarily, such as for maintenance of MongoDB, or during the peak load time to prevent impacting the performance of MongoDB. In the next screen, we will discuss customized data distribution. A MongoDB administrator can control sharding by using tags. Tags help control the balancer behavior and chunks distribution in a cluster. As an administrator, you can create tags with the ranges of shard keys and assign them to the shards. The balancer process migrates the tag data to the shards that are assigned for those tags. Tag-aware sharding helps you improve the locality of data for a sharded cluster. In the next screen, we will discuss tag-aware sharding. In MongoDB, you can create tags for a range of shard keys to associate those ranges to a group of shards. Those shards receive all inserts within that tagged range. The balancer that moves chunks from one shard to another always obeys these tagged ranges. The balancer moves or keeps a specific subset of the data on a specific set of shards and ensures that the most relevant data resides on the shard which is geographically closer to the client application server. In the next screen, we will discuss how to add shard tags. When connected to a MongoS instance, use the sh.addShardTag method to associate tags with a particular shard. A single shard may have multiple tags, whereas multiple shards may have a common tag. Consider the example given on the screen. This adds the tag NYC to two shards, and adds the tags SFO and NRT to a third shard. To assign a tag to a range of shard keys, connect to the MongoS instance and use the sh.addTagRange method. Any given shard key range may only have one assigned tag. You cannot overlap defined ranges or tag the same range more than once. A collection named users in the records database is sharded by the zip code field. The following operations assign 2 ranges of zip codes in Manhattan and Brooklyn, the NYC tag, 1 range of zip codes in San Francisco, the SFO tag. Note that the shard key range tags are distinct from the replica set member tags. Hash-based sharding only supports tag-aware sharding on an entire collection. Shard ranges include the lower value and exclude the upper value. In the next screen, we will discuss how to remove shard tags. To remove shard tags, you first need to view the existing shard tags. Typically, shard tags exist in the shards document in a collection of the config database. To return all shards with a specific tag, use the operations as given on the screen. This will return only those shards that are tagged with NYC. You can find tag ranges for all the namespaces in the tags collection of the config database. The output of sh.status displays all tag ranges. To return all shard key ranges tagged with NYC, use the following sequence of operations given on the screen. The MongoDB facilitates removing a tag range. To delete a tag assignment from a shard key range, remove the corresponding document from the tags collection of the config database. Each document in the tags holds the namespace of the sharded collection and a minimum shard key value. The third example given on the screen removes the NYC tag assignment for the range of zip codes within Manhattan. Here is a quick recap of what was covered in this lesson. Replication is recommended in the production setting to increase data availability and redundancy. Replica sets are recommended for new production deployments to replicate data in a cluster. A typical replica set in MongoDB consists of 1 primary and 2 secondaries. In addition to the primary and secondary, a replica set can have an arbiter, a priority 0 member, a hidden member, and a delayed member. Consider deploying a sharded cluster when the data set exceeds the storage capacity of a single MongoDB instance, the size of the active working set exceeds the capacity of the maximum available RAM, or a single MongoDB instance is unable to manage the right operations. To deploy a sharded cluster, start the config server database instances, and then start the 3 config server instances. Shard balancing is a background process that manages chunk migration for an even distribution of data shards in a cluster. This concludes the lesson, Replication and Sharding. In the next lesson, we will discuss developing Java and Node.js applications using MongoDB. Hello and welcome to Lesson 6 of the MongoDB Developer course offered by Simplilearn. Welcome to Lesson 6 of the MongoDB Developer course offered by Simplilearn. This lesson will explain the process of developing Java and Node.js applications using MongoDB. Let us explore the objectives of this lesson in the next screen. After completing this lesson, you will be able to explain a capped collection, explain how Grid File System, or GridFS, is used for storing large data, explain how to create a connection and perform the CRUD operation using Java Node.js applications, identify the steps to install the Java driver, explain the process to create a collection from a Java program, and explain the procedure to use the Java program to perform functions such as insert, update, and retrieve. In the next screen, we will begin with what capped collections are. Capped collections in MongoDB are collections with predefined sizes and support operations that insert and retrieve documents. Capped collections function like circular buffers. Once a collection fills its allocated space, it overwrites older documents to allocate space for new documents. Capped collections exhibit the following behaviors. They preserve an insertion order. Therefore, queries can return documents in the insertion order without the help of an index. This helps them support higher insertion throughput. They ensure that the insertion order functions similar to the order on the disk or the natural order. They do so by prohibiting updates that increase document size. It allows only those updates that fit the original document size. This ensures that a document location on the disk remains unaltered. Capped collections delete the oldest documents in a collection automatically. They do not require scripts or explicit remove operations to do so. In the next screen, we will discuss how to create a capped collection. To create a capped collection, you need to use the Create Collection method explicitly. When creating a capped collection, you need to specify the maximum size of the collection in bytes. MongoDB will pre-allocate the size for the collection. The size must include space for the internal overhead. Use the syntax given on the screen to specify the size. If the specified size field is less than or equal to 4096 bytes, then the collection will have a cap of 4096 bytes. Otherwise, MongoDB will increase the size to make it an integer multiple of 256 bytes. Additionally, you may also specify the maximum number of documents for the collection using the max field as shown on the screen. We will continue our discussion on capped collection creation in the next screen. When creating a capped collection, you need to do the following. Query a capped collection. If you perform the find query on a capped collection without specifying any order, MongoDB ensures that the ordering of results is the same as the insertion order. To retrieve documents in the reverse insertion order, issue the find query along with the sort method and set the natural parameter to -1 as shown in the example given on the screen. Check if a collection is capped. Use the isCapped method as given in the command on the screen to determine if a collection is capped. Convert a collection to capped. Convert a non-capped collection to a capped collection with the Convert to Capped command. In the next screen, we will view a demo on how to create a capped collection. This demo will show the steps to create a capped collection in MongoDB. In this demo, you will learn how to create a capped collection in MongoDB. Let us create a collection named Web Server Log. This collection will contain maximum 5,000 documents, and its size will be 5 megabytes. To create a capped collection, execute the command shown on the screen. To verify whether the Web Server Log collection is created or not, execute the Show Collection command. To verify whether the collection is a capped collection, use the isCapped method as shown on the screen. If you want to convert an existing collection into a capped collection, then you need to use Convert to Capped option in the Run command as shown on the screen. In this command, you are converting the items collection into a capped collection of fixed size of 100,000 bytes. To verify whether the collection is a capped collection or not, use the isCapped method as shown on the screen. This concludes the demo on creating a capped collection in MongoDB. When updating a capped collection, you can make only in-place updates to documents. If the update operation increases the original document size, the operation does not succeed. To update documents in a capped collection, first create an index to avoid a table scan. When you update a document to a smaller size than the original document size, a secondary resyncs from the primary. The secondary replicates and allocates space based on the current size of the updated document. However, if the primary receives an update which restores the original document size, the primary accepts the update whereas the secondary fails. The secondary receives the error message, "Objects in a capped NS cannot grow." Note that you cannot remove documents from a capped collection. However, you can remove all documents from a collection by dropping the entire collection using the drop method. You also cannot shard a capped collection. In the next screen, we will discuss the TTL collection features. For a capped collection, data is automatically removed once the collection grows beyond the threshold size and the number of documents defined. To allow flexibility for expiring data, consider MongoDB's Time to Live or TTL indexes. TTL indexes help delete data from normal collections using a special type field and a TTL value for the index. For TTL collections, MongoDB automatically removes data after a specified duration of time in seconds or at a specific clock time. Note that TTL collections are not compatible with capped collections. A special TTL index property supports the implementation of TTL collections as shown on the screen. In the next screen, we will view a demo on how to create TTL indexes in MongoDB. This demo will show the steps to create TTL indexes in MongoDB. In this demo, you will learn how to create a TTL index in MongoDB. You need to create a TTL index on the created at field of the existing collection named Web Server Log that will delete the documents after 1 hour or 3,600 seconds. To create the TTL index, execute the command shown on the screen. To automatically delete documents at a specific clock time, create a TTL index on a field that holds BSON date type values or an array of BSON date typed objects. In addition, specify the expire after seconds value as 0. To create a TTL index on the expire at field of the Web Server Log collection, execute the command shown on the screen. Now, you can insert a document into this collection and specify the clock time for expiring document. Use the command shown on the screen to specify the value of expire at June 30th, 2015, 1400 hours. This value indicates that the document will be deleted on June 30th, 2015 at 1400 hours. This concludes the demo on creating a TTL index collection in MongoDB. GridFS is a specification used for storing and retrieving files exceeding 16 megabytes, the BSON limit for document size. GridFS splits a file into different parts or chunks and stores each unit as a separate document. The default chunk size specified by GridFS is 255 kilobytes. Typically, GridFS stores files in two collections. In one collection, the file chunks are stored while the metadata is stored in the other collection. When returning a query result from GridFS, the driver or client reassembles the chunks as required. You can perform range queries on files stored in GridFS. For example, you can skip into the middle of a video or an audio file to access information. GridFS allows you to access any files without having to load the entire file into memory. In the next screen, we will discuss GridFS collection. You can store and retrieve files from GridFS using either of the following tools: a MongoDB driver, the Mongo Files command line tool in the Mongo shell. GridFS stores files in two collections. fs.chunks store the binary chunks. fs.files store the file's metadata. You can choose a different bucket name and also create multiple buckets in a single database. Each document in the chunks collection represents a distinct chunk of a file as represented in the GridFS store. Each chunk is identified by its unique object ID stored in its _ID field. GridFS index. GridFS uses a unique compound index on the chunks collection for the files _ID and N fields. The files _ID field contains the _ID of the chunk's parent document. The N field contains the sequence number of the chunk. GridFS numbers all chunks, starting with 0. For the descriptions of the documents and fields in the chunks collection, the GridFS index allows efficient retrieval of chunks using the files _ID and N values, as shown in the following example given on the screen. If your driver does not create this index, issue the following operation given on the screen using the Mongo shell. In the next screen, we will view a demo on how to insert an image in MongoDB from a Java application. This demo will show the steps to insert an image in MongoDB from a Java application. In this demo, you will learn how to insert images into MongoDB from a Java application. Let us view a Save Image app written in Java, which will store images into MongoDB using the GridFS function. For this, first establish a connection with MongoDB server by creating a new Mongo object. The object constructor takes the IP address and port number as the parameter. A butterfly image stored at the C drive will be inserted into the photo collection. This will be inserted as a document with the file name field as GridFS Java image. In the code shown on the screen, the GridFS's create file and save method is used to store the image into the photo collection. Next, run the Java application. The output displayed on the screen shows that the image is inserted into MongoDB with a chunk size as 262,144. Next, Go to the Mongo shell to verify whether the image is stored in the photo collection of Image Database 1. To do so, execute the command given on the screen. The output shows that the image is inserted as a document, which has the file name gridfs Java image. The binary content of the image in the chunks collection is also shown by executing command shown on the screen. To view the different fields of inserted image, execute the command as shown on the screen. Metrics such as chunk size, length, MD5, content type, upload date, and file name printed are shown on the screen. To view the binary data stored for this image in the chunks collections, use the command given on the screen. This concludes the demo on inserting an image into MongoDB from Java application. Applications communicate with MongoDB through client libraries or drivers that handle all the interactions with the database in a language that is appropriate and sensible. The following languages are used for communication: JavaScript, Python, Ruby, PHP, Perl, Java, Scala, C++ Haskell, and Erlang. In the next screen, we will discuss how to develop a Java application with MongoDB. MongoDB used the Java driver from its earliest versions. Because of its stability, the Java driver is the popular choice among enterprise developers. To install the Java driver, perform the following steps. Step 1. The Java driver comes as a jar file. You can download this jar file from the link given on the screen. Step 2. Add the jar file to your class path. The Java classes you need to use in a normal application are in the com.mongodb and com.mongodb.gridfs packages. The jar file contains a number of other packages. You need these packages only to either modify the driver's internal functionality or extend its functionality. In the next screen, we will discuss how to connect to MongoDB from a Java program. To create a normal Java application, you need to first create a new Java project in Eclipse and add the MongoDB Java driver into its build and class path. The Java driver of MongoDB provides the com.mongodb.mongo class to create a connection to the MongoDB server. To establish a connection, you need to create a new Mongo object and pass the IP address and port number of the MongoDB server as a parameter, as shown in the code given on the screen. Once a Mongo object is created, you can create a Mongo client instance to access the database and perform create, retrieve, update, delete, or CRUD operations. In the next screen, we will discuss how to create a collection from a Java program. You can create a collection from a Java program using the create collection method of the com.mongo.db class. A DB object instance is created from the return object of the Mongo client.getDB method. The code shown on the screen is used for first connecting to the MongoDB server by creating a Mongo client object. After a Mongo client object is created, specify the name of the database in the getDB method call of the Mongo client object, and then connect to the database. Use the DB object to call the create collection method to create a collection in MongoDB. In the next screen, we will discuss how to insert documents using a Java program. Typically, documents in Java must be instances of org.bson.db object, an interface that is an ordered java.util.map. A document can be created in multiple ways in Java. However, the simplest way to create one is using the com.mongodb.basicDBObject class. To create a document that is represented by the shell as item book, sold quantity 500, use the command given on the screen. In the next screen, we will discuss how to insert documents using the Java code example. To insert a document in a collection, you need to first create an instance of the DB collection object. You can do so by calling the getCollection method of the DB object. To represent the JSON document in the Java code, you need to create basic DB object. In addition, you must call the append method to set the values for all the fields that need to be populated. After basic DB object is initialized, call the insert method of DB collection. This inserts the document into the collection by passing basic DB object as a parameter. In the next screen, we will view a demo on inserting a document using Java. This demo will show the steps to insert a document in a collection using Java. In this demo, you will learn how to insert a document in a collection using Java. To create a normal Java application, first create a new Java project in Eclipse and add MongoDB Java driver into its build and class path. In the given code, you are importing MongoDB classes such as Mongo Client, DB, DB collection, and basic DB object. The insert class contains the main method in which you write the codes to connect to the database. Using Mongo class, you can create a connection to a MongoDB server. To establish a connection, you need to create a new Mongo client object and pass the IP address and port number of MongoDB server as the parameter as shown in the code. Once the Mongo client object is created, you can connect to the database by specifying test as the name of the database to be connected in the getDB method call of the Mongo client object. Next, you need to use the DB object to call createCollection and create a collection items in MongoDB. To insert a document into a collection, create an instance of basic DB object and provide all the fields in the append method. Finally, use the insert call of the insert method in DB collection. For error handling, try and catch block is included. Next, run the application by selecting Run as Java Application. In the console, you can see the statement printed. This confirms that the insert operation is successful. Next, go to the Mongo shell and execute the command db.item.find to view the inserted documents. This concludes the demo on inserting a document in a collection using Java. The db.collection update method is used to update an existing document in a collection. For updating documents, you can use the update methods of db collection. In the code given on the screen, the db cursor object is used to iterate through the list of documents in the while loop and update each document by inserting the field like with its value as 200. In the next screen, we will view a demo on how to update a document in a collection using Java. This demo will show the steps to retrieve a document from a collection using Java. In this demo, you will learn how to retrieve a document from a collection using Java. Using the code shown on the screen, you are importing MongoDB classes such as Mongo Client, DB, DB Collection, and Basic DB Object. In the Retrieving Documents class, you have the main method. Using the Mongo class, you can create a connection to a MongoDB server. To establish a connection, you need to create a new Mongo Client object. Once the Mongo Client object is created, connect to the database by specifying test as the name of the database to be connected in the getDB method call of the Mongo Client object. Next, use the DB object to call getCollection to get a collection items from MongoDB. To retrieve a document from the collection, you need to call the find method of DB Collection object. The find method returns the DB cursor object, which is used to iterate over documents. In the while loop, you are printing some statements to confirm retrieval of documents by calling the cursor.next method. For error handling, try and catch block are included. Run this application by selecting the Run as Java Application option. In the console, you can view document values such as title MongoDB and likes 200. This concludes the demo on retrieving a document from a collection using Java. The db.collection update method is used to update an existing document in a collection. For updating documents, you can use the update methods of DB collection. In the code given on the screen, the DB cursor object is used to iterate through the list of documents in the while loop and update each document by inserting the field like with its value as 200. In the next screen, we will view a demo on how to update a document in a collection using Java. This demo will show the steps to update a document in a collection using Java. In this demo, you will learn how to update a document in a collection using Java. Using the code shown on the screen, you are importing MongoDB classes such as Mongo Client, DB, DB Collection, and Basic DB Object. In the Update Documents class, you have the main method. Using Mongo class, you can create a connection to a MongoDB server. To establish a connection, you need to create a new Mongo Client object. Once the Mongo Client object is created, connect to the database by specifying test as the name of the database to be connected in the getDB method call of the Mongo Client object. Next, use the DB object to call getCollection to get a collection items from MongoDB. To update a document from the collection, you need to call the find method of the DB Collection object. The find method returns the DB cursor object, which can be used to iterate over documents. In the while loop, you can get the DB object by calling the cursor.next method and then adding likes as a field and 1500 as the value. To update the document, you need to call the update method of the DB collection object by passing the search query and update document as the parameter. The search query is the basic DB object wherein you have specified the query condition. Next, call the find method to verify whether the document is updated or not. For error handling, include try and catch block. Run the application by selecting Run as Java Application. In the console, you will view the document values and that the value for likes is updated to 1500. This concludes the demo on updating a document in a collection using Java. To remove documents from a collection, use the DB Collections Remove method. In the code given on the screen, you are retrieving the document to be deleted by calling the find_one method. You are also passing the retrieved document in the remove method as a parameter to remove it from the collection. In the next screen, we will view a demo on how to delete a document using Java. This demo will show the steps to delete a document from a collection using Java. In this demo, you will learn how to delete a document from a collection using Java. In the code given on the screen, you are importing MongoDB classes, such as Mongo Client, DB, DB Collection, and Basic DB Object. In the Delete Documents class, you have the main method. Using Mongo class, you can create a connection to a MongoDB server. To establish a connection, you need to create a new Mongo Client object. Once the Mongo Client object is created, connect to the database by specifying test as the name of the database to be connected in the getDB method call of the Mongo Client object. Next, use the DB object to call getCollection to get a collection items from MongoDB. To delete a document from the collection, you need to call the remove method of the DB collection object. In the remove method, you need to pass the search query, which is the basic DB object having the title as the field and MongoDB as the value. Here, you are calling the find method to verify whether the document is deleted or not. For error handling, include try and catch block. Next, run the application by selecting Run as Java Application. In the console, the printed statement shows that the document is deleted. This concludes the demo on deleting a document from a collection using Java. In the code shown on the screen, Save Image App, written in Java, will store images into MongoDB using the gridfs function. For this, first establish a connection with the MongoDB server by creating a new Mongo object. This object constructor takes the IP address and port number as parameters. To insert an image into MongoDB, you need to create an instance of the gridfs object by passing the DB instance and the collection name as parameters. Next, you need to pass the image path to the createFile method of the gridfs object to store the image. Here, you are storing a butterfly image from the C drive into the photo collection. This image will be inserted as a document with the file name field as gridfs Java image. In the next screen, we will discuss retrieving images using gridfs API. To retrieve all the DB cursor objects having reference to the file stored in gridfs, you can use a gridfs object instance and call the getFileList method. You can then iterate through each file in the while loop to print all file names. In addition, you can use the find_one method of gridfs to fetch the files based on the file names. This will return the gridfsDB file object. In the next screen, we will discuss how to remove images using gridfs API. To remove the image file from gridfs, you can use an instance of the gridfs object and call the remove method. In the next screen, we will discuss MongoDB with Node.js. To work with a database, you first need to create a connection. You can use MongoDB's native Node.js driver to create a connection with the MongoDB server. To install the MongoDB native drivers, first install the MongoDB module using the npm command. Next, run the command given on the screen in your project directory. npm is a package manager. It provides a central repository for custom open-source modules for Node.js and JavaScript. npm helps manage modules, their versions, and distribution easily. The npm install command is used to install the required module in a project. In the next screen, we will discuss how to create a connection using Node.js. To create a connection using Node.js, perform the following steps. Step 1. To create a connection to the database, first load the MongoDB module. The code given on the screen uses require to load the MongoDB module. The MongoDB module represents the native MongoDB drivers for Node.js. Step 2. Define the URL you need to connect to. You need to know where the MongoDB server is running. The URL provides the location where the MongoDB server instance is running. The URL also contains the database name to which you want to connect. Step 3. Connect to the database. Use the Mongo Client Interface's connect method to connect to the database. In the callback, you either get an error or get the DB object. Use the DB object to communicate with the database. In the next screen, we will discuss how to perform insert operations using Node.js. After you have a DB connection ready, you can communicate with the database. You can perform some basic operations on the MongoDB database. When using the MongoDB native driver, you need to ensure that the query function names and their parameters are similar to that of the native MongoDB commands. The query functions take the callback as the last argument. The callback function returns the first argument as an error and the second argument as a result. The result is actually the result or output provided by MongoDB on running these commands. This is similar to the results you get when you run these queries in the MongoDB shell. In the next screen, we will continue our discussion on performing the insert operation using Node.js. Suppose you need to create an items collection and save a few items in it. For this, you will use the insert method to save the item's information. In the code shown on the screen, you perform the following steps. You use the db.collection method to get the reference to your items collection. If the collection does not exist, then it will be created on the first insert. If it already exists, then you will be working on the existing one. You need not to explicitly create a collection. Prepare data to be inserted. You created some sample item record objects named Item 1, Item 2, and Item 3. There is no fixed schema of the document. They are simple JS objects with the entity's data. Insert into the database. You use collection.insert to insert your data in the database collection. You passed an array of items to it, and it saved all of them in one step. In the subsequent screens, we will view demos on performing CRUD and inserting and retrieving operations. This demo will show the steps to perform CRUD operations in Node.js. In this demo, you will learn how to perform CRUD operations in Node.js. You used require to load the MongoDB module in the code. MongoDB module represents the native MongoDB drivers for Node.js. Let us use the Mongo Client Interface's connect method to connect to the database. In the callback, you will either get an error or the DB object. Use the DB object to communicate with the database. Let us look at the code for inserting documents into MongoDB. Let us assume that you need to create a user's collection and save a few users in it. For this, use the insert method to save the user info. Get the reference of your user's collection. You use the db.collection method to get the reference of user's collection. If the collection does not exist, then it will be created on the first insert. You created some sample users record objects named User1, User2, and User3. There is no fixed schema of the document. They are simple JS objects with entities data. You use the collection.insert method to insert data in the database collection and passed an array of users to it, and it saved all of them in one step. Here, in this code, you have a if-else block to print the log message for the failure and print the document's length for successful insert operation. To see the code for retrieving documents from MongoDB, go to queryusers.js using Node.js. To do so, use the find method of the collection object. In this code, toArray is used to find. Using the find alone returns a DB cursor. You will need to iterate over the cursor and fetch results. For performance reasons, MongoDB does not fetch the full record data by default. Using toArray tells the driver to fetch the full data of each item, which is then returned. In this code, too, you have written if, and else block to print the log message for the failure, print the document's length if document is found, and print empty document if document is not found. This concludes the demo on performing CRUD operations in Node.js. This demo will show the steps to perform insert and retrieve operations in Node.js. In this demo, you will learn how to perform insert and retrieve operations in Node.js. To run the Node.js program, you need to type node program_name. Here, you are using the Node Mongo Create connection to run the program. The connection has been established with MongoDB running on the local host. Let us create a collection and insert some documents into it. For this, run the createusers.js file by typing node createusers.js. The result displayed on the screen shows all inserted documents and other driver-related configuration information. Once user documents are inserted into the collection, you can run node queryusers.js to retrieve these documents. The result displayed shows the details of all the user documents. This concludes the demo on performing insert and retrieve operations in Node.js. You can update records using the collection.update method. The name and parameters of the update method are similar to that of native MongoDB queries. The code given on the screen updates the documents from Node.js. In the next screen, we will discuss retrieving documents using Node.js. To retrieve documents from MongoDB, trigger the find command on the collection object just as in the MongoDB shell. The example given on the screen is used for retrieving a document. In this code, toArray is used along with the find method. Running the find method alone returns a DB cursor. You will need to iterate over the cursor to fetch the results. For performance reasons, MongoDB does not fetch the complete record data by default. Using toArray tells the driver to fetch full data of each item. In the next screen, we will discuss how to use the DB cursor to retrieve documents. You can use the DB cursor instead of each document or use toArray to return the full array of all documents. Using each will load the documents with each iteration. In addition, some other methods are available, such as remove to delete documents, count to count the number of documents, and so on. In the next screen, we will discuss the Mongoose Object Design Management, or ODM, module. Mongoose.js is a popular library in Node.js. It provides a straightforward schema-based solution to model your application data and includes built-in typecasting, validation, query building, business logic hooks, and so on. Using the Mongoose interface features such as automatic connection and connection pool management, you can easily work with MongoDB. To work with Mongoose, you need to first install the Mongoose module. run the npm install mongoose command to install the mongoose module. In the next screen, we will discuss how to define a schema using mongoose. In the code shown on the screen, you are doing the following things. Connecting to the database. You use the mongo.connect method to connect to the desired database. Mongoose.js will then internally handle the connection and the connection pool as configured. Creating a model. You create a model using the mongoose.model method. The model represents a collection in the database. The name you provide to the model will be pluralized internally, and the collection with that plural name will be created in MongoDB. For example, if you name the model user, then the collection will be named users with lowercase. You can also define the schema for a document during this process. We will continue our discussion on defining schema using Mongoose in the next screen. You perform the following action using the code given on the screen. Create a new user object. You can create a new user object using the model. You can create as many user objects using the model as desired. Each object will represent a document in the database. In addition, you can modify and save the object. Save the user using the save method. The Mongoose model has many methods available on the entity objects. In this case, you will use the save method to save the document in the database. You can also use the model to query the database. To query the database collection, you can use the model defined to do that. In the example given on the screen, you try to find a user and then update it. In the next screen, we will view a demo on using Mongoose to define a schema. This demo will show the steps to define a schema and perform insert and query operations using Mongoose in Node.js. In this demo, you will learn how to define schema, insert, and query operation using Mongoose in Node.js. In the code shown here, you are using the mongoose.connect method to connect to the desired database. The mongoose.js will then internally handle the connection and connection pool as configured. Next, you are creating a model using the mongoose.model method. The model represents a collection in the database. You are creating a new user object using a model. You can then create as many user objects using the model. Each object created will represent a document in the database. Next, you use the save method to save the document in the database. Let us look at the code of querying document using Mongoose in the Node.js. To query the database collection, you can use the defined model. Here, you can use the find1 method and pass the query condition as name modulus admin. In this part of the code, you are updating the document to add the value 30 into its age field. This concludes the demo on defining schema, insert, and query operation using Mongoose in Node.js. This demo will show the steps to run the Node.js application to perform insert and query operations using Mongoose in Node.js. In this demo, you will learn how to run the Node.js application to perform insert and query operations using Mongoose in Node.js. Run mongoose.js to insert the document into MongoDB by typing node mongoose.js. From the output displayed on the screen, you can see that user document is inserted into MongoDB. Next, query the document by executing the command node query_mongoose.js. The result displayed on the screen shows the user document with its fields such as name, age, and roles. This concludes the demo on running the Node.js application to perform insert and query operations using Mongoose in Node.js. Here is a quick recap of what was covered in this lesson. Capped collections in MongoDB contain collections with predefined sizes that support insert and retrieve operations. When creating a capped collection, you need to specify the size, query a collection, check if the collection is capped, and convert a collection to capped. The gridfs specification splits a file into different parts or chunks and stores each unit as a separate document. To install the Java driver in MongoDB, you need to add the jar file to your class path. You can create a collection from a Java program using the createCollection method of the com.mongodb.db class. You can use the DB cursor instead of each or use the toArray to return the full array of all documents. You can use the native MongoDB module and Mongo client to connect to MongoDB from Node.js. You can use the db.collection method to get the reference to your collection and then use insert, find, and delete methods. This concludes the lesson, Developing Java and Node.js Application with MongoDB, the last lesson of the MongoDB Developer course. Hello, and welcome to Lesson 7 of the MongoDB Administrator course offered by Simply Learn. This lesson will explain the administrative features of MongoDB. Let us explore the objectives of this lesson in the next screen. After completing this lesson, you will be able to explain capped collection, explain how grid file system, or GridFS, are used for storing large data, explain what memory mapped files are, explain allocation algorithms, describe the storage engines MongoDB supports. In the next screen, we will begin with what capped collections are. Capped collections in MongoDB are collections with predefined sizes and support operations that insert and retrieve documents. Capped collections function like circular buffers. Once a collection fills its allocated space, it overwrites older documents to allocate space for new documents. Capped collections exhibit the following behaviors. They preserve an insertion order. Therefore, queries can return documents in the insertion order without the help of an index. This helps them support higher insertion throughput. They ensure that the insertion order functions similar to the order on the disk or the natural order. They do so by prohibiting updates that increase document size. It allows only those updates that fit the original document size. This ensures that a document location on the disk remains unaltered. Capped collections delete the oldest documents in a collection automatically. They do not require scripts or explicit remove operations to do so. In the next screen, we will discuss how to create a capped collection. To create a capped collection, you need to use the Create Collection method explicitly. When creating a capped collection, you need to specify the maximum size of the collection in bytes. MongoDB will pre-allocate the size for the collection. The size must include space for the internal overhead. Use the syntax given on the screen to specify the size. If the specified size field is less than or equal to 4096 bytes, then the collection will have a cap of 4096 bytes. Otherwise, MongoDB will increase the size to make it an integer multiple of 256 bytes. Additionally, you may also specify the maximum number of documents for the collection using the max field as shown on the screen. We will continue our discussion on capped collection creation in the next screen. When creating a capped collection, you need to do the following. Query a capped collection. If you perform the find query on a capped collection without specifying any order, MongoDB ensures that the ordering of results is the same as the insertion order. To retrieve documents in the reverse insertion order, issue the find query along with the sort method and set the natural parameter to -1 as shown in the example given on the screen. Check if a collection is capped. Use the isCapped method as given in the command on the screen to determine if a collection is capped. Convert a collection to capped. Convert a non-capped collection to a capped collection with the Convert to Capped command. In the next screen, we will view a demo on how to create a capped collection. This demo will show the steps to create a capped collection in MongoDB. In this demo, you will learn how to create a capped collection in MongoDB. Let us create a collection named Web Server Log. This collection will contain maximum 5,000 documents, and its size will be 5 megabytes. To create a capped collection, execute the command shown on the screen. To verify whether the web server log collection is created or not, execute the show collection command. To verify whether the collection is a capped collection, use the isCapped method as shown on the screen. If you want to convert an existing collection into a capped collection, then you need to use Convert to Capped option in the Run command as shown on the screen. In this command, you are converting the items collection into a capped collection of fixed size of 100,000 bytes. To verify whether the collection is a capped collection or not, use the isCapped method as shown on the screen. This concludes the demo on creating a capped collection in MongoDB. When updating a capped collection, you can make only in-place updates to documents. If the update operation increases the original document size, the operation does not succeed. To update documents in a capped collection, first create an index to avoid a table scan. When you update a document to a smaller size than the original document size, a secondary resyncs from the primary. The secondary replicates and allocates space based on the current size of the updated document. However, if the primary receives an update which restores the original document size, the primary accepts the update whereas the secondary fails. The secondary receives the error message, "Objects in a capped NS cannot grow." Note that you cannot remove documents from a capped collection. However, you can remove all documents from a collection by dropping the entire collection using the drop method. You also cannot shard a capped collection. In the next screen, we will discuss the TTL collection features. For a capped collection, data is automatically removed once the collection grows beyond the threshold size and the number of documents defined. To allow flexibility for expiring data, consider MongoDB's Time to Live or TTL indexes. TTL indexes help delete data from normal collections using a special type field and a TTL value for the index. For TTL collections, MongoDB automatically removes data after a specified duration of time in seconds or at a specific clock time. Note that TTL collections are not compatible with capped collections. A special TTL index property supports the implementation of TTL collections as shown on the screen. In the next screen, we will view a demo on how to create TTL indexes in MongoDB. This demo will show the steps to create TTL indexes in MongoDB. In this demo, you will learn how to create a TTL index in MongoDB. You need to create a TTL index on the created at field of the existing collection named Web Server Log that will delete the documents after 1 hour or 3,600 seconds. To create the TTL index, execute the command shown on the screen. To automatically delete documents at a specific clock time, create a TTL index on a field that holds Beeson date type values or an array of Beeson date typed objects. In addition, specify the expire after seconds value as 0. To create a TTL index on the expire at field of the Web Server Log collection, execute the command shown on the screen. Now, you can insert a document into this collection and specify the clock time for expiring document. Use the command shown on the screen to specify the value of expire at June 30th, 2015, 1400 hours. This value indicates that the document will be deleted on June 30th, 2015 at 1400 hours. This concludes the demo on creating a TTL index collection in MongoDB. GridFS is a specification used for storing and retrieving files exceeding 16 megabytes, the Beeson limit for document size. GridFS splits a file into different parts or chunks and stores each unit as a separate document. The default chunk size specified by GridFS is 255 kilobytes. Typically, GridFS stores files in 2 collections. In one collection, the file chunks are stored while the metadata is stored in the other collection. When returning a query result from GridFS, the driver or client reassembles the chunks as required. You can perform range queries on files stored in GridFS. For example, you can skip into the middle of a video or an audio file to access information. GridFS allows you to access any files without having to load the entire file into memory. In the next screen, we will discuss GridFS collection. You can store and retrieve files from GridFS using either of the following tools: a MongoDB driver, the Mongo Files command line tool in the Mongo shell. GridFS stores files in 2 collections. fs.chunks store the binary chunks. fs.files store the file's metadata. You can choose a different bucket name and also create multiple buckets in a single database. Each document in the chunks collection represents a distinct chunk of a file as represented in the GridFS store. Each chunk is identified by its unique object ID stored in its _ID field. GridFS index. GridFS uses a unique compound index on the chunks collection for the files _ID and N fields. The files _ID field contains the _ID of the chunk's parent document. The N field contains the sequence number of the chunk. GridFS numbers all chunks, starting with 0. For the descriptions of the documents and fields in the chunks collection, The grid FS index allows efficient retrieval of chunks using the file's _ID and end values, as shown in the following example given on the screen. If your driver does not create this index, issue the following operation given on the screen using the Mongo shell. In the next screen, we will view a demo on how to insert an image in MongoDB from a Java application. This demo will show the steps to insert an image in MongoDB from a Java application. In this demo, you will learn how to insert images into MongoDB from a Java application. Let us view a Save Image app written in Java, which will store images into MongoDB using the grid FS function. For this, first establish a connection with MongoDB server by creating a new Mongo object. The object constructor takes the IP address and port number as the parameter. A butterfly image stored at the C drive will be inserted into the photo collection. This will be inserted as a document with the file name field as grid FS Java image. In the code shown on the screen, the grid FS's create file and save method is used to store the image into the photo collection. Next, run the Java application. The output displayed on the screen shows that the image is inserted into MongoDB with a chunk size as 262,144. Next, go to the Mongo shell to verify whether the image is stored in the photo collection of Image Database 1. To do so, execute the command given on the screen. The output shows that the image is inserted as a document, which has the file name gridfs Java image. The binary content of the image in the chunks collection is also shown by executing command shown on the screen. To view the different fields of inserted image, execute the command as shown on the screen. Metrics such as chunk size, length, MD5, content type, upload date, and file name printed are shown on the screen. To view the binary data stored for this image in the chunks collections, use the command given on the screen. This concludes the demo on inserting an image into MongoDB from Java application. A memory-mapped file contains data stored by the operating system in its memory. This file uses the mmap system call to store data. The mmap method maps the file to a region of virtual memory. Memory-mapped files are the critical pieces of the mmap version 1 storage engine in MongoDB. The memory-mapped files enable MongoDB to treat the contents of its data files as if they were in the memory. This enables MongoDB to access and manipulate data faster. MongoDB uses the memory-mapped files to manage and interact with all types of data. Memory mapping assigns data files to a virtual memory block having a byte-for-byte correlation. As and when accessing documents, the MongoDB memory maps them. Therefore, only accessed data is mapped to the memory, whereas the data that is not accessed is not memory mapped. Once memory mapping is complete, the relationship between the file and memory allows MongoDB to interact with the data in the file as if it were in the memory. In the next screen, we will discuss journaling mechanics. MongoDB uses write operations before logging into an on-disk journal. This ensures the strength of write operations. Before making any changes to the data files, MongoDB first performs the change operation in the journal. If a MongoDB instance encounters any error or terminates before writing the changes from the journal to the data files, MongoDB can reapply the write operation to maintain a consistent state. If a MongoDB instance exits unexpectedly without a journal, this means that your data is not consistent. You must then run a repair or, preferably, resync from a clean member of the replica set. When journaling is enabled, even if MongoDB stops unexpectedly, the program can recover all the written data to the journal. The recovered data is in a consistent state. By default, the writes lost by MongoDB, the writes that were not made to the journal, are made in the last 100 milliseconds. If journaling is enabled, and if you have sufficient RAM in your system, the entire data set and the write working set can reside in the RAM. To enable journaling, start MongoDB with the Journal command line option. In the next screen, we will discuss Storage Engine. A storage engine of a database manages how data is stored on a disk. Typically, databases support multiple storage engines, each engine performing specific workloads. For example, one storage engine may manage read-heavy operations, whereas another may support a higher throughput for write operations. With multiple storage engines available, you can choose one that best suits your application. In the next screen, we will discuss mmap version 1 storage engine. mmap version 1 is a storage engine based on memory-mapped files. This storage engine can manage high-volume operations, such as inserts, reads, and in-place updates. mmap version 1 is the default storage engine in MongoDB 3.0 and all previous versions. To ensure that all data set modifications are stored on the disk, MongoDB records all modifications in a journal. It writes to the disk more frequently than it writes the data files. The journal lets MongoDB recover data from data files after a MongoDB instance exits without making all changes. In the next screen, we will discuss Wired Tiger Storage Engine. In MongoDB version 3.0, an additional storage engine is available. Although mmap version 1 remains the default storage engine, the new Wired Tiger engine offers additional flexibility and improved throughput for many workloads. The Wired Tiger storage engine is optionally available in the 64-bit build of MongoDB version 3.0. This engine supports high volumes of read, insert, and more complex update workloads. Document-level locking. All write operations in Wired Tiger occur within the context of a document-level lock. Therefore, multiple clients can simultaneously modify more than one document in a single collection. With such control, MongoDB can effectively support read, write, update, and high-throughput concurrent workloads. For data persistence, Wired Tiger uses a write-ahead transaction log in combination with various checkpoints. Using Wired Tiger, MongoDB commits a checkpoint to the disk either every 60 seconds or when there are only 2 gigabytes of data to write. The checkpoint thresholds are configurable, and all data files between and during the checkpoints are always valid. The Wired Tiger journal persists all data modifications between the checkpoints. If MongoDB exits between the checkpoints, it enables the journal to replay all the data modified since the last checkpoint. By default, the Wired Tiger journal is compressed using the Snappy algorithm. In the next screen, we will discuss Wired Tiger compression support. MongoDB uses block and prefix compressions to support compression for collections and indexes. Compression minimizes the storage use at the cost of an additional CPU. By default, prefix compression is used for all indexes in the Wired Tiger engine. In addition, by default, all collections with Wired Tiger use block compression combined with the Snappy algorithm. Compressions with zlib are also available. You can modify the default compression settings for all collections and indexes. During collection and index creation, you can configure compressions on per collection and per index basis. For most workloads, the default compression settings balance storage efficiency and processing requirements. In the next screen, we will discuss the power of two-sized allocations. MongoDB version 3.0 uses the power of two-sized allocation as the default record allocation strategy for the mmap version 1 storage engine. With this strategy, each record has a size in bytes that is a power of 2. For example, 32, 64, 128, 256, 512 kilobytes, and 2 megabytes. For documents larger than 2 megabytes, the allocation is rounded up to the nearest multiple of 2 megabytes. The power of two-sized allocation strategy has the following key properties. Can reuse freed records and reduce fragmentation. Quantizing record allocation sizes in a fixed set of values ensures that an insert will fit into the free space available due to deletion or relocation of earlier documents. Can reduce moves. The added padding space gives a document scope to grow without requiring a move. In addition to saving the cost of moving, this results in few updates. In the next screen, we will discuss no padding allocation strategy. For some collections, the workloads that consist of insert-only or update operations do not increase or change the document sizes. For such workloads, you can disable the power of two allocation using the collection modification command with the no padding flag or the db.createCollection method with the no padding option. Prior to version 3.0, MongoDB used an allocation strategy that included a dynamically calculated padding as a factor of the document size. In the next screen, we will discuss how to diagnose performance issues. Degraded performance in MongoDB is typically a function that depicts a relationship among the following: the quantity of data stored in the database, the amount of available system RAM, the number of connections to the database, and the amount of time the database spends in the locked state. The performance issues in some cases are momentary and relate to traffic load, data access patterns, or the availability of hardware in the host system for virtualized environments. The performance issues are also the results of inadequate or inappropriate indexing strategies and poor schema design patterns. In other situations, performance issues may indicate that the database requires additional capacity. We will continue with our discussion on diagnosing performance issues in the next screen. The following are some causes of performance degradation in MongoDB. Locks. To ensure data set consistency, MongoDB uses locks. However, if certain operations run for longer durations or queue up, performance degrades because requests and operations wait for a lock. Lock-related slowdowns can be irregular. To know if a lock affects your database performance, review the data in the global lock section of the server status output. If global lock.currentQueue.total is consistently high, then it is possible that a large number of requests are waiting for a lock. This indicates that a possible concurrency issue is affecting your database performance. Memory usage. MongoDB uses memory-mapped files to store data. For a data set of a sufficient size, the MongoDB process allocates all the available memory to the system. This is a part of the design for MongoDB's enhanced performance. However, the memory-mapped files make it difficult to determine if the amount of RAM is sufficient for a data set. To determine the MongoDB's memory usage, check the memory usage statuses metrics of the server status output. You can also check the resident memory using the mem.resident command. If this exceeds the system memory, and there is a significant amount of data on the disk that is not in the RAM, that means that you have exceeded the capacity of your system. In addition, check the amount of the mapped memory, mem.mapped. If this value is greater than the system memory, some operations may require to read data from the virtual memory. This will negatively impact the system performance. We will discuss some more performance issues in the next screen. Some more causes of performance issues are page faults. When the mmap version 1 storage engine is used, page faults occur as MongoDB reads from or writes data to the data files that are not located in its physical memory. On the contrary, operating system page faults occur when the physical memory is exhausted and pages of the physical memory are swapped to the disk. Page faults triggered by MongoDB are reported as the total number of page faults in 1 second. To check for page faults, view the extra_info.page_faults value in the server status output. Page fault counters in MongoDB may increase drastically when poor performance happens and may correlate with the limited physical memory environments. Page faults can increase when accessing larger data sets, such as scanning an entire collection. Limited and sporadic page faults in MongoDB do not necessarily indicate an issue and do not require any corrective measure. To reduce the page fault frequency, increase the RAM in MongoDB. Alternatively, deploy a sharded cluster or add shards and distribute loads among MongoDB instances. Number of connections. The server's ability to handle a request depends on the number of connections between the application layer and the database. If the number of connections is too high, This can result in performance irregularities. If the number of requests is high because of numerous concurrent application interactions, the database may not be able to meet the demand. In such a case, you need to increase the capacity of your deployment. For read-heavy applications, increase the size of your replica set and distribute read operations to secondary members. For write-heavy applications, deploy sharding and add one or more shards to a sharded cluster and distribute the load among MongoDB instances. MongoDB has no limit on incoming connections unless it is constrained by system-wide limits. In the next screen, we will view a demo on monitoring performance in MongoDB. This demo will show the steps to monitor performance in MongoDB. In this demo, you will learn how to monitor MongoDB performance. The MongoStat utility captures and returns the counts of database operations by their types. For example, insert, update, and delete. To get a report on the load distribution of the server, execute the MongoStat command. MongoTop is another utility that tracks and reports the current read and write activities of a MongoDB instance. To track all the read and write activities, type MongoTop. Let us connect to the Mongo shell to use some of the Mongo shell commands to monitor MongoDB. For this, type Mongo. To get a general overview of the database status, execute the db.serverStatus command. This command returns quickly and does not impact MongoDB performance. To get an overview of the database storage use and data volumes, execute db.stats from the shell. This returns a document that shows the amount of storage used, the quantity of data contained in the database, object, collection, and index counters. Next, execute the command given on the screen to retrieve information, such as the objects in the collection, the size of the collection, the amount of disk space used by the collection, and its indexes. This concludes the demo on monitoring MongoDB performance. Many factors can affect the database performance and responsiveness. These include index usage, query structure, data models, and application design. In addition, operational factors such as architecture and system configuration can also affect the database performance. The following techniques are used for evaluating the operational performance of MongoDB. Database Profiler. MongoDB provides a database profiler that can be used to identify the performance characteristics of each operation against the database. For example, using the profiler, you can identify the queries or write operations that are running slow. You can use this information to determine what indexes to create. Capped collections. Capped collections are circular, fixed-size collections that help keep documents in a proper order even without the use of an index. Capped collections receive very high-speed writes and sequential reads. For faster write operations, use capped collections. Natural order. To return documents in the order they exist on the disk and return sorted operations, use the natural operator. On a capped collection, this also returns the documents in the order in which they were written. The natural order does not use indexes, but enables faster operations when you want to select the first or the last item from the disk. In the next screen, we will discuss how to configure tag sets for replica sets. You can configure tag sets in a replica set using the following methods. db.currentOp. Use this method to evaluate MongoDB operations. This method reports the current operations running on a MongoDB instance. Cursor.explain and db.collection.explain. Use these explain methods to evaluate a query performance, such as the index MongoDB selects to fulfill a query and its execution statistics. You can run the methods in the following three modes to control the amount of information returned: Query Planner, Execution Stats, All Plan Execution. In the next screen, we will discuss how to optimize query performance. You can optimize query performance in the following ways. Create indexes to support queries. Typically, scanning an index is much faster than scanning a collection. For commonly issued queries, create indexes for quick returns. To search for multiple fields, create a compound index for the query. The index structures are smaller than the document's reference and store references in an order. Limit query results to reduce network demand. MongoDB cursors return results in groups of multiple documents. To get the desired number of results, use the limit method to reduce the demand for network resources. For example, to get 10 results from a query to the posts collection, issue the following command given on the screen. Use projections to return only necessary data. To receive a subset of fields from documents, you can choose to have better performance by returning only the required fields. For example, for the post collection query, you need the timestamp, title, author, and abstract fields. Therefore, you would issue the following command given on the screen. Use hint to select a particular index. You can force MongoDB to use a specific index using the hint method. Use the hint method on queries where you must select the fields included in several indexes to support performance testing. Use the increment operator to perform operations server-side. If a field is a type number, then use the inc operator to increment or decrement values in documents. This operator executes the logic at the server side rather than making changes at the client side before sending the whole document to the server. This operator also helps avoid race conditions. In the next screen, we will discuss the monitoring strategies used in MongoDB. Monitoring is a critical component of the entire database administration. The following three strategies are used for collecting data and monitoring a MongoDB instance. Utilities are distributed with MongoDB that provides real-time reporting of database activities. Database commands return statistics regarding the current database state with greater reliability. MMS monitoring collects data from the running MongoDB deployments and provides visualization and alerts based on that data. Note that these strategies are complementary. Each strategy can help answer different questions and is useful in different contexts. In the next screen, we will discuss MongoDB utilities. MongoDB includes a number of utilities that quickly return statistics about the performance and activity of an instance. Typically, these are useful for diagnosing issues and assessing a normal MongoDB operation. These utilities are as follows. MongoStat. It captures and returns the counts of database operations by type. For example, insert, query, update, delete, and so on. These counts report the load distribution of the server. You can use MongoStat to understand the distribution of operation types and to inform capacity planning. MongoTop. The MongoTop utility tracks the current read and write activities of a MongoDB instance and reports their statistics on a per-collection basis. You can use MongoTop to check whether your database activity matches your expectations. HTTP Console. MongoDB provides a web interface for receiving diagnostic and monitoring information in a simple web page. You can access this web interface from localhost ;port. Here, the port number is 1000 more than the MongoD port. For example, if a locally running MongoDB is using the default port 27017, you will be able to access the HTTP console from the link given on the screen. In the next screen, we will discuss MongoDB commands. MongoDB uses a number of commands that report the state of the database. This data may provide a finer level of granularity than the utilities. You can use their output in scripts and programs to either develop custom alerts or to modify the behavior of your application. The commands are as follows. db.currentOp. This method helps to identify the in-progress operations of a database instance. Server status. The server status command or the db.serverStatus method from the shell returns an overview of the database status. This command provides details of the disk usage, memory usage, connection, journaling, and index access. The command returns quickly and does not impact the MongoDB performance. dbstats. This command, when executed from the shell, returns a document that addresses the storage usage and data volumes. dbstats reflects the amount of storage used, the quantity of data contained in the database, object, collection, and index counters. Collection stats. The collection stats, or db.collection.stats method, executed from the shell, provides statistics, such as the number of documents in the collection, size of the collection, hard disk utilization by the collection, and information regarding its indexes. Replica set getStatus, or rs.status from the shell, returns an overview of the replica set status. This command provides details of the state and configuration of the replica set, and also provides statistics about its members. These metrics are very useful to check whether a replica set is properly configured or not. Ganglia MongoDB. Ganglia is the Python script for viewing a replica set information, such as memory usage, B-tree statistics, master-slave status, and current connections. In addition, mtop, Munin, and Nagios are the tools used to check server statistics and scripts. In the next screen, we will discuss MongoDB Management Service, or MMS. MMS is a cloud service that helps monitor, backup, and scale MongoDB on the infrastructure of your choice. You can monitor more than 100 system metrics and get custom alerts before your system starts degrading. You can create your own alerts and integrate monitoring with the tools you already use. In the next screen, we will discuss the data backup strategies in MongoDB. When you deploy MongoDB in production, you should have a strategy for capturing and restoring backups to prepare for the data loss events. You can perform a backup of MongoDB clusters in the following ways. Backup by copying the underlying data files. Backup a database with MongoDump. Use the MMS Cloud Backup. In the next screen, we will discuss copying underlying data files. You can create a backup for MongoDB by copying its underlying data files. If the volume where MongoDB stores data files supports point-in-time snapshots, you can use these snapshots to create backups of a MongoDB system at the exact moment of time. File system snapshots are not specific to MongoDB. The mechanics of snapshots depend on the underlying storage system. On a Linux computer, the Logical Volume Manager, or LVM, can create a snapshot. To get a correct snapshot of a running MongoDB process, you must enable journaling. The journal must reside on the same logical volume as the other MongoDB data files. If journaling is not enabled, there is no guarantee that the snapshot will be consistent or valid. To get a consistent snapshot of a sharded cluster, first disable the balancer and capture a snapshot from every shard and the config server simultaneously. If your storage system does not support snapshots, you can copy the files directly using the copy command in Linux, rsync, or a similar tool. Copying multiple files is not an atomic operation. Hence, stop all the writes to MongoDB before copying the files. Otherwise, the files will be copied in an invalid state. Backups created by copying the underlying data do not support point-in-time recovery for the replica sets and are difficult to manage for larger, sharded clusters. These backups are huge because they include the indexes and duplicate the underlying storage padding and fragmentation. MongoDump, on the other hand, creates smaller backups. In the next screen, we will discuss backup with MongoDump. The MongoDump tool reads data from a MongoDB database and creates BSON files. The MongoRestore tool populates a MongoDB database with the data from these BSON files. These tools are simple and efficient for backing up small MongoDB deployments. However, they are not suitable for backing up for larger systems. MongoDump and MongoRestore can operate against a running MongoDB process. These tools can manipulate the underlying data files directly. By default, MongoDump does not capture the contents of the local database. It only captures the documents in the database. Although the resulting backup is space efficient, MongoRestore or MongoDB must rebuild the indexes after restoring data. When connected to a MongoDB instance, MongoDump can adversely affect the MongoDB performance. If your data volume is larger than the available system memory, the queries will push the working set out of the memory. To mitigate the impact of MongoDump on the performance of the replica set, use MongoDump to capture backups from a secondary member of the replica set. Alternatively, you can shut down a secondary and use MongoDump with the data files directly. If you shut down a secondary to capture data with MongoDump, ensure that the operation completes before its oplog is unable to replicate. To restore a point-in-time backup created with oplog, use MongoRestore with the oplog replay option. If applications modify data while MongoDump is creating a backup, MongoDump will compete for resources with those applications. In the next screen, we will discuss fsync and lock. MongoDump and MongoRestore allow you to perform data backups without shutting down the MongoDB server. However, you lose the ability to get a point-in-time view of the data. MongoDB's fsync command allows you to copy the data directory of a running MongoDB server without any risk of corruption. The fsync command forces the MongoDB server to send all the pending writes to the disk. Optionally, it also prevents any further writes to the database until the server is unlocked. This write lock feature makes the fsync command suitable for backups. The example given on the screen shows how to run the command from the shell, forcing an fsync and acquiring a write lock. At this point, the data directory represents a consistent point-in-time snapshot of your data. Because the server is locked for writes, you can safely make a copy of the data file system, such as LVM, which allows a quick snapshot of the data directory. After performing the backup, unlock the database again using the command given on the screen. Next, run the current op command to ensure that the lock is released. Note that it may take a moment after unlock is first requested. The fsync command allows you to perform a flexible backup without shutting down the server or sacrificing the point-in-time nature of the backup. The only way to have a point-in-time snapshot without any downtime for reads or writes is to back up from a slave. In the next screen, we will discuss Ops Manager, the backup software in MongoDB. MongoDB Operations Manager is a service that allows you to manage, monitor, and back up the MongoDB infrastructure. Operations Manager provides the following services. Operations Manager Backup provides scheduled snapshots and point-in-time recovery of your MongoDB replica sets and sharded clusters. This backup creates snapshots of the standalones that are run as single-member replica sets. MMS has a lightweight backup agent that runs within your infrastructure and backs up data from the MongoDB processes you have specified. In the next screen, we will discuss security strategies in MongoDB. To maintain a secure MongoDB deployment, you need to implement controls and ensure that users and applications have access to only those data required for their job roles. MongoDB provides various features that allow you, as an administrator, to implement these controls and restrictions for deploying any MongoDB instance. Following are some of the security strategies in MongoDB. Authentication. It is the mechanism for verifying a user and instance access to MongoDB. Authorization. This allows you to control a user or application access to MongoDB instances. Collection-level access control. This allows scope privileges to specific collections. Network exposure and security. It discusses potential security risks related to the network and strategies for decreasing the possible network-based attack vectors for MongoDB. Security and MongoDB API interfaces. This allows you to reduce and control the potential risks related to MongoDB's JavaScript, HTTP, and REST interfaces. Auditing. It includes audit server and client activities for MongoD and MongoS instances. In the next screen, we will discuss authentication implementation. Before gaining an access to a system, clients should identify themselves to MongoDB. This ensures that a client cannot access the MongoDB data without authentication. MongoDB supports various authentication mechanisms to enable clients to verify their identities. It supports a password-based challenge, response protocol, and X509 certificates. Additionally, MongoDB Enterprise provides support for lightweight Directory Access Protocol, or LDAP proxy authentication, and Kerberos authentication. X509 certificate authentication. This authentication mechanism was introduced in MongoDB version 2.6. It supports X509 certificate authentication for use with a secure SSL connection. For server authentication, clients can use X509 certificates instead of usernames and passwords. For membership authentication, members of sharded clusters and replica sets can use X509 certificates instead of key files. Kerberos authentication. MongoDB Enterprise 8 supports Kerberos service authentication. This is an industry standard authentication protocol for large client-server systems. To use MongoDB with Kerberos, you must have a properly configured Kerberos deployment and Kerberos service principals, and add Kerberos user principal to MongoDB. LDAP proxy authority authentication. MongoDB Enterprise supports proxy authentication through an LDAP service. In the next screen, we will discuss authentication in a replica set and sharded cluster. You can authenticate the members of replica sets and sharded clusters. To authenticate the members of a single MongoDB deployment to each other, use the key file and X509 mechanisms. When you use the key file authentication, this also enables the authorization for members. You also need to run replica sets and sharded clusters in a trusted networking environment. Ensure that the network permits only trusted traffic to reach each MongoD and MongoS instance by using a firewall and network routing, virtual private networks or VPNs, or wide area networks or WANs. In addition, always ensure that your network configuration allows every member of the replica set or sharded cluster to contact every other member. The key file configuration is done on all the members to permit authentication. In the next screen, we will discuss authentication on sharded cluster. In sharded clusters, applications authenticate directly to MongoDB instances using the credentials stored in the admin database of the config servers. The shards in the sharded cluster also have credentials, and clients can authenticate directly to the shards to perform maintenance on the shards. In general, applications and clients should connect to the sharded cluster through the MongoDB. Some maintenance operations, such as cleanup orphaned, compact, and rs.config, require direct connections to the specific shards in a sharded cluster. To perform these operations with authentication enabled, you must connect directly to the shard and authenticate as a shard local administrative user. To create a shard local administrative user, connect directly to the shard and create the user. MongoDB stores shard local users in the admin database of the shard itself. These shard local users are completely independent from the users added to the sharded cluster via MongoDB. Shard local users are local to the shard and are inaccessible by MongoDB. Direct connections to a shard should only be for shard-specific maintenance and configuration. In the next screen, we will discuss authorization. Access control or authorization defines a user's access to a system's resources and operations. Ideally, users should be able to perform only those operations that are required to fulfill their defined job roles. This is the principle of least privilege that controls and limits the potential risk of a compromised application. MongoDB's role-based access control system allows you as an administrator to control all user access and ensures that all the granted access applies as narrowly as possible. MongoDB does not enable authorization by default. When you enable authorization, MongoDB requires authentication for all the connections. After authorization is enabled, MongoDB controls each user access through its assigned role. Each role consists of a set of privileges, and each privilege consists of actions, a set of operations, and resources. Every user may have one or more assigned roles that describe its access. MongoDB provides several built-in roles, such as the read, read-write, dbadmin, and root roles. Users can also have customized roles suited to clients' requirements. MongoDB does not enable authorization by default. You can enable authorization using the auth or the key file options. If you are using a configuration file, you can enable authorization with the security.authorization or the security.key file settings. You can also create new roles and privileges to cater to operational needs. You can assign privileges scoped as granularly as the collection level. When you grant a role to a user, the user receives all the privileges associated with the role. A user can have several concurrent roles, and in such cases receives all the privileges of the respective roles. In the next screen, we will discuss end-to-end auditing for compliance. As an administrator, you need to implement security policies to control the activities in a system. Auditing enables you to verify that the implemented security policies are controlling the activities as desired. Retaining the audit information ensures that you have enough information to perform forensic investigations and comply with the regulations and policies that require the audit data. The auditing facility allows you and other users to track a system activity for deployments with multiple users and applications. The auditing facility can write audit events to the console, the syslog, a JSON file, or a BSON file. Here is a quick recap of what was covered in this lesson. Capped collections in MongoDB contains collections with predefined sizes that support insert and retrieve operations. When creating a capped collection, you need to specify the size, query a collection, check if the collection is capped, and convert a collection to capped. The gridfs specification splits a file into different parts or chunks and stores each unit as a separate document. Gridfs uses two collections, fs.files and fs.chunks. A memory mapped file contains data stored by the operating system in its memory. MongoDB supports multiple storage engines such as mmap version 1 and Wired Tiger, and allows you to choose the one best suited to your needs. The causes of performance issues in MongoDB include locks, memory usage, page faults, and number of connections. This concludes the lesson Administration of MongoDB Cluster Operations, the last lesson of the MongoDB Administrator course.